All right, I was going over where to access the stuff that we went over last time in Blackboard. All right. Still learning names and faces. Mason, okay. Now, some faces I try to forget as soon as possible. No, I'm just kidding. Okay. What's that? Yeah, I'm just going to show you. It's out there now. Yeah, I did it over between my last two classes. Yeah, last class and this class. All right. Here we go. Physical Science 112, Spring 16-17. Okay. First and foremost, now your home page may not look exactly like this, because this is the instructor side, you see the student side. I don't see the student side, so I don't know how yours look. But it's probably somewhat similar. If you go down here to the third blue tab, or whatever color yours is, under Content, click on that, and then you'll get the syllabus, and you can read the syllabus. I've updated it. I think everything is correct now, okay? Research paper instructions. I've corrected those that we talked about last time, and those are out there. My locator card, I've corrected that. It's out there. The Chapter 1 PowerPoints that did last time and will continue doing today, they're out there. As well as Chapter 2 PowerPoints, 3 PowerPoints, 4 PowerPoints, 6 PowerPoints, and 8 PowerPoints. But then at the very bottom here, you'll see Physical Science 112 videos. Okay? I'll go on and click on it now, just to show you where to go on it. And this is a little bizarre, so don't get too lost with it. What I've done, just in case you wanted to look ahead, these top several videos are the ones I taught from last fall. They're not this time. It's the same material, and you'll hear me say some of the same things, maybe a little bit differently. Those first ones are those are from last fall. But if you scroll on down to the bottom, because that's where it puts it, this is the one I did last time. Physical Science Syllabus and Chapter 1. Okay? We got started in Chapter 1. Then the one that I'll do today, that I'm already recording today, that will, when I load this, and it'll probably be sometime tomorrow, it'll go up here, it'll say Chapter 1, probably Chapters 1 through 2 with Lab 1, something like that. Once I load that one, I'll take this one off, because there's no reason to duplicate. But the new one will be at the bottom. These are the old ones at the top. Okay, so you can access anything we have covered, and basically a lot of what we will cover, you can look at those. But the ones I'm doing, new ones, are at the bottom, not at the top. Okay, so you should be able to access those. All right, I'll go on and sign out of this and get out of that. And no, it doesn't do a good job of that. The old package we used to use, Tegrity, yeah, it had the dates, it had everything you needed. This one, just remember the newest stuff's at the bottom, starting with the syllabus. Anything below the syllabus is new, and anything above that is the older stuff. But rather than reorder every time, rearrange, and then I might get confused as which is which. I keep them in that order so I know which ones.
Put the date in the title. You think that will help?
I don't. They're limited to so many characters. If I could, I'll try to. I'll see if I run out of characters. I'll try doing that. But they only limited you to so many characters. I think I've got enough to do it. I haven't ever reached the max, so it should be able to do so. All right. And remind me of your name?
Samuel.
Samuel, got it. Okay. I know I've seen your name here. There it is, right at the end. Okay, of the first page. Okay, good deal. So that should take you up to speed. Now, if you go to the one that we did last time, you'll hear me talk about the syllabus. talk about the research paper, instructions, talk about my locator card, talk about safety issues, and then we got started in chapter 1. Okay? We got a decent way through, more than halfway through chapter 1. All right, and so, sort of to fill you in. Remember the syllabus was here, the research paper instructions here, the locator cards here, and the videos are here. The PowerPoints are here. But you get to see them all again there because I talk about them there. So this is actually, to me, would be the better place. But if you wanted to, say, print those off ahead of time or something like that so you can take notes on them, fine, go for it. But they're there in case you need them for any other purposes. Now, let me say this, too. I can't remember if I said this last time. Let's see. I don't think I need Blackboard anymore. Okay? But I want y'all to hear it. Spread it around among your friends. And it's on this, too. I do allow you to bring to any test a formula and equation sheet. Anything you want to write on a piece of paper, front and back, you can bring with you to every test. Okay? Any test. Okay? So I don't think this is a memorization course. If you are working for me, I don't want you trying to memorize formulas. I want you looking them up, make sure you got the right one, if you're doing something. So that's just how I approach things, and so that's how I would suggest. In fact, I recommend this. In any course, I know y'all are almost through your program, but in any course you take, or are taking now or will be taking, I highly recommend doing a formula and equation sheet, even if you can't use it. Because the few times as an undergraduate that I was allowed to have one, man, that night before I was writing things, as small as I could read, getting it organized so I'd know where to find it and stuff, and putting that thing together. And the next day when I went to take the test, I hardly looked at it because I had it all, I'd just done it, and that was the best study tool I had ever come up with. And I thought, why didn't I think someone tell me this sooner, because quite often I'd almost forget to look at it because I'd just done all that work, organization and stuff like this. So when you're taking tests, not about it. Now, don't use it if you're not allowed to use it, but do it as part of your study. All right. Any questions before we get started on where we left off last time? So let me do one other thing before we do get started. Well, I thought it was going to start from this slide. There we go. Like there was some other announcement doesn't pertain to this class. It was on midterm progress reports. This is just getting started, so you wouldn't have one there. And the other thing is my new office hours, but I've already told you my new office hours because y'all are just getting started. And y'all are the reasons I have new office hours, because I was starting at 12:30, now at 1:15. Okay. All right, let's talk about the sequence of things. We will finish chapter 1 pretty easily today. There's not that much left in the chapter. There is a fair amount, but we got 2.5 hours of class before, quote, lab time. So we will finish chapter 1, but then rather than doing the lab on chapter 1 and then coming back and doing chapter 2, what I'll do is just keep on trucking into chapter 2. And then when it gets time for lab time, now today, I'll say this. The first lab in this course is the longest, most involved, in many ways maybe most difficult. It's abstract. I don't know why they put the biggest, toughest lab right at the beginning. But I'll be with you there and we'll go through it, okay? So it actually may be we might not finish the lab today, okay? If we don't, we'll allow time on Tuesday to finish it. But we'll try to get it done today. The trouble is my work-study student is next door doing Scholars Bowl, and he wasn't available to help me set up the lab any. And I just barely had time to get all the stuff done on Blackboard, eat lunch, and get here. So because my computer down in my office was not reading the CD, so I couldn't load it on the Blackboard. I had to come up here and use this one, and then I got interrupted several times when students saw me up here. So anyway, So today we'll finish chapter 1, get started in chapter 2, and the last 2 hours of the day, 3:45 until 5:45, we will have the lab for chapter 1. Tuesday, we'll continue chapter 2. My guess will get far enough along so we can have the first lab in chapter 2. So on Tuesday's class, it'll be only 2 hours of class, 2 hours of lab, and then the last 30 minutes will be the test on chapter 1. Let me say this about the test in chapter 1. It's different from all the other tests also. Probably more calculations, not that many, but more calculations than you'll see on most of the tests. More fill in the blank than you'll see on just about any of the tests. And very few, but a few multiple choice. Most of your other tests, the other 5 tests, chapters 2, 3, 4, 6, and 8, will be mostly multiple choice, with a few problems and a few fill in the blanks. Okay? The first test, though, I tried to use their test bank, and it was just really poor for this chapter, so I had to expand on it, and you'll see. But we're going to do problems like, the math that we're going to do. In fact, that's where we're going to start today. All right, and then after that, the labs, none of the rest of the labs will be as long as the days. Some of them will be fairly short, so when you have 2 hours for lab, you'll probably finish in less than 2 hours. If you have the test right after, you can start the test when you finish the lab, and when you finish the test, you're free to go, So that's why I put the labs and the test at the end, so that if you finish early, you can go early. I don't want to have you doing a test early and then sitting around waiting for everybody else to do the test, and then we get started and go until 5:45. So I tried to do it so it'll be best on your schedules, because I know several of you have a fair ways to go. All right, now what I missed last time was I skipped over some of the examples, and these are some problem-solving type things, like I won't say you'll have the same ones, but you have things similar to this on the test. Now let me see if I can find, great blank page to do on. So if you got your books, I only see 1 or 2. What's that?
They thought the 111 was the same as the 112. But he told me to let you know that he ordered them. He put in 2-day shipping, so might be here Friday, but Monday for the special.
I did a book order and I put the right numbers on it, and he said he understood, and then he screwed it up. He doesn't belong to the college. I don't know if you know that. About a year or so ago, they decided to go with a outside thing, so they haven't been all that great. But if he said he'll do, what's that?
They got a ton of 111, but no 112.
Well, I put in both of them and specified. Well, but we've been doing that for several terms. It's nothing new to them. They just screwed up. I'm sorry about that. What's that?
I gotta switch mine out when they get the.
Oh, you got 111 too?
Yeah.
See, they kept telling me that the 111 was the same, but I told him, he told me to make sure it say 112. And that's when he started going through his computer, this, that, another, that he realized that they have different information.
When I got this book the day before our first class, this was the last 112, this was 111.
But he told me and he said that to let you know that he put in for 2-day shipping. He said so it should be either Friday or Monday.
I'm sorry about that, folks. The book order went in correctly. They just screwed it up. Sorry, but they don't belong to the college, so we have to live with them. They sort of do whatever they want to, and it's really discouraging to hear they're giving such poor service. But he said he did 2 days, so hopefully they'll be here. Now, it sounds like to me it's probably going to be the bigger book. In the big book, the same book covers both courses. The little ones, though, and he's known that because I was using the little ones to save them money. I mean, it saves you money, but it saves them money too. They're just reselling them over and over and over, So he knew it. I don't know. They canned the guy, and it may be he's the one that screwed it up. I don't know. But they should have caught it by now. All right, let's go. We're on page 9. in chapter 1. It's an example 1. 2 blocks are on a table. Now, my drawings stink, but I really suggest pictures are worth, I always thought the saying went, a picture's worth 1,000 words. So when I would say, I'd say pictures are worth thousands of words, because my words are pretty bad. My pictures are pretty bad too. But then I found out just recently the actual saying was a picture is worth 10,000 words. So whatever, but pictures are worth a lot, and even if they're ugly. So let's say we've got a table here, okay? I don't draw well at all, so okay. There's our table. And on the table, we have 2 blocks. Here's a block, and there's a block, okay, on the table. Pretty ugly, huh? Block A has a volume, so I'm going to call it VA, of 30.0 cubic centimeters. Good measurement for volume. And it has a mass, so the mass for block A is 81 grams. Now, time out here. If it's 30 cubic centimeters, 81 grams, why are they putting those extra zeros on there?
To let you know that it's a even number or a solid number.
That what?
To let you know it's a solid number.
Let you know that what?
It's a solid number.
Okay. Actually, pretty close, but here's what it means. Say again? The precision is to the third digit. In other words, that's not just like 29.8. This is 30.01. I mean, that would be, it's good to 3 decimal place, or 3 digits, 3 significant digits on each of those. Why do they do that? Then when you do your answer, even though when you do things on the calculator, it give you a string of digits that long, don't give me all those digits. Only do the number that the problem has, 3 digits, okay? Now, block B, on the other hand, here's block B. It has a volume, so volume for block B would be 50.0 cubic centimeters. The mass for B would be 135 grams. Notice they don't put a 0.0 there because that has 3 significant digits right there. Okay. Which block has the greater density? Anyone want to make a guess? A or B?
You say A.
You say A? Everybody agree with him? Okay. How do we calculate density? What is the formula for density? Density for A is mass per unit volume. So that would be mass of A divided by volume for A. And anyone got a calculator? Second, 2.70. Very good. Grams per cubic centimeter. Keep your units. 2.70 tells me it's a number. I put the extra 0, even though I bet you on your calculator it was 2.7, wasn't it? But you wisely put the 0 because we got 3 significant digits. How about the density for B? That would be the mass for B divided by the volume for B. It's the same, isn't it? 2.70 grams per cubic centimeters. What does that sort of tell you? Probably the same material. Density is an intrinsic property of any substance, and therefore if that substance is that substance, it's going to have the same density, whether you have a little or a lot, has the same density. And if you have your books, which none of you do, and look at table 1.3, densities of some common substances, aluminum, 2.70 grams per cubic centimeter. Of all of our metals, this is one of the lightest. Okay? What's the ramification for that? Say again? Okay, yeah, it's probably not as strong, but generally it's strong enough. You've been watching those Ford commercials, haven't you? No, I won't say that. Okay. What's the advantage? You said it wasn't strong, so that, huh? Okay, and what does light do for you? Say again? Okay, you're absolutely right. Most of the airplanes, if you've ever flown, you probably flew in a predominantly aluminum aircraft. Let's just look at some of the others. Copper, which is in most of your wiring, that's 8.96 grams per cubic centimeter. That's between 2 and 3 times as dense as aluminum. Iron, 7.87, still more than twice as dense. Lead, 11.4, that's approaching 5 times as dense. Now water, of course, is what? 1.00 grams per cubic centimeter. That's the standard. Remember, when they first figured out what, in the metric system or SI system, a meter, and then they went to centimeters, and then a cubic centimeter, they said, what will we name our masses in? Grams. So they took the most common substance on the surface of the earth, which was water, and said, we'll name that 1 gram. 1 cubic centimeter of water will be 1 gram. So that's why it has a density of 1 gram per cubic centimeter. Seawater is just a slight bit denser, right? What's the ramification? It's 1.03. What's the ramification of that? It's salty, you're right. But you also float better in it, don't you? Have you ever noticed pool versus ocean? You float better in the ocean because it's denser water. Huh?
So I don't float in either of them.
Yeah, I used to not. I think I was a sinker. I think I probably barely float now. Now, another ramification of that, a boat that goes both sea and saltwater, freshwater and saltwater. In freshwater, it'll sink down further. It floats better too. So sometimes on ships that do both, you'll see 2 water lines there that indicate, displacement and stuff. One for seawater and one for freshwater. Mercury, 13.6 grams per cubic centimeter. Densest thing on a table so far. It's not the densest thing out there. Pretty dense. What's unusual about mercury? It's a liquid, yeah. It's a liquid metal, but it's denser than many of the solid metals. So in other words, lead, which is 11.4, will float in mercury. Believe it or not, it floats in mercury. Don't try it. Lead will float in mercury. Yeah, a lot of the heavy metals, besides the music, they are toxic, okay? Yeah, that's pretty toxic too. I don't know, I didn't say that, did I? Okay, but the heavy metals are, both lead and mercury, you don't want to be in. Now, lead is a solid, it's not going to rub off on you or anything, but mercury being a liquid, you don't want to mess around. I can remember when I was in school, someone would have some from somewhere, and we put a penny in it, and it would turn silvery looking and look like a dime, and do all this stuff, and it beat it up, and it was sort of fun. It was hazardous. We didn't know it at the time. You don't want to mess around with it. In fact, they had a mercury spill over in the physics lab on the Birmingham campus, and they had to quarantine the lab. And it wasn't that much either, but they had to pull out all the wood that had sucked up the mercury and replace it, so it's not stuff to mess around with. What's that? Yeah, I don't know if they did. I assume they did. I wasn't there when they had the spill. And here's Terry. Right. Okay. All right. Finally, the last thing in the table, now these are all the things out there, but gasoline has a density of 0.608. What's the ramification of that? Yes, it's less dense than water. So if you have water in your gas, where is it going to be? It's going to be at the bottom, the gas at the top. So if you're pulling the stuff out of the bottom of the tank, that's going to be water. pull it off the top, that'll be gas. When you get the water, you're still in problems. But in the old, like small engines and stuff like this, they used to have the little, in fact, tractors used to have a little, the bowl there, and you can, and you can see if there's water in your gas and take it and dump it out. Say again?
They still have it.
I can't.
They still have it.
They still, I knew the tractors but most of our tractors on the farm now are diesel, so we don't have that many gasoline tractors anymore. Say again?
Diesel still got it. Diesel
Diesel actually has them too now.
Diesel.
Really? Okay, I hadn't seen that on the diesels.
On the tractor.
Yeah, I'm not on the farm that much anymore, so I'm not involved with it that much. But anyway, so we probably had aluminum on the table there. And what's the other ramification? Yeah, we already said the gas floats, so it'll always be on the surface. And most of the oils will float and greases will float because they're less dense than water. Let's do example 1.2. That was 1.1. A rock with a volume, so a volume of a rock. And by the way, for those who weren't here last time, the little m, that's just what we use to stand for mass. These are the parameters. The capital V is volume because most of the time in the next chapter or two, we'll be hitting this. Little v stands for velocity, capital V for volume. So that's why we did that. And that funny looking symbol there is not a P, that's a rho. Okay? It's a Greek letter, a lowercase case, pretty much corresponds to our R. Looks more like a P, but that's the density formula. Okay. So here's a rock, has a volume of 4.5 cubic centimeters. 4.50 cubic centimeters. Okay? And a mass of 15 grams. What is the density of the rock? Pretty straightforward, same as before. Density of that rock would be, anyone got a calculator? Yes, approximately 3.33 grams per cubic centimeter. Again, don't ever just give me a number. Always have a unit. Now, your calculator kept going forever, didn't it? 3. You only have 3 significant digits here. Stop it at 3. And you know rounding, right? Count to the digit you're interested in. The third digit, look to the right. If it's less than 5, leave it as it is. If it's more than 5, bump this up a lot. 5 or greater, bump it up. All right. They have a little concept supplied here too. How dense is your textbook approximately? Okay. Now later we'll probably do some densities. I can't remember if we do in this class or not. But sometimes what we do there is take the mass of the thing, and then to get density we displace it in water. We don't want to do that to our books, okay? So they said the best thing to estimate this, length times width times thickness, that's, do that all in centimeters if you're using SI units, and then that's the volume, so you estimate the density that way. You can do that if you'd like. They have also in the text these little blurbs, mistakes and misunderstandings. And they talk about tapping on a can, talking mostly about aluminum cans, I think, most of the time. They believe that tapping on the side of a can will prevent it from foaming over when you open. Any validity to that? I can't imagine why. They have just little things like this, so they tell you how to do a little experiment to test on that. Now, I do know this, and this, you were talking about strength of aluminum. You can stand on an aluminum can. If you're careful to stand on it, it will support you. Just that little lightweight aluminum can. But if you're doing that or someone else is, you can go to the side and tap on the sides then with someone standing on it, and it'll collapse in a moment because its strength is in the fact that the sides are rigid and no dents in them. But once it has a dent, then it collapses like crazy. I'm not suggesting you try that, but it's sort of fun. Yeah. What's that?
So they always stand on when they crush.
Well, yeah, if you stomp on them and stuff, you can. But if you're careful,
If you're careful, even if
you can stand on it. It stands right up there. What's that?
So if you're not careful, it'll fold you inside first, and then
You talking
Yeah.
about you drunk the beer, though.
Oh, yeah, he's still got beer in his. No, I wasn't talking about that kind of can. No, okay.
That in your mouth, like,
I didn't want you wobbling. I wanted you standing still. Never mind. Okay. All right. There's other concepts applied here, and this is one that I really did mean to talk about. I wish you had your books, but hopefully they will be here soon. I would go down and fuss at the bookstore right after class, but I'm sure they'll be closed then. I'll not be here tomorrow, and by Monday I'll forget about it. But anyway, I want to fuss at them. Okay. Have you ever heard of an inverse squared relationship? What that might mean. Okay. Here's an example. My wife loves these little night lights that she can clip on her book or her Kindle, and then she can read in bed at night. I like it too that she doesn't have the light on, but anyway, and it's plenty bright, in fact, very bright, but it just, a little light. Well, why doesn't she hang that from the ceiling and read in bed that she won't have it clipped on her book? Would it work? No, it's too far away, because light decreases in magnitude by an inverse square law. Now, what do we mean by that? This was back when we were talking about direct proportion and inverse proportions. Inverse proportion, the further you are away, the dimmer it is. The closer you are, the brighter it is, okay? No, well, the distance is inversely proportional, okay, to the brightness. Okay, but not just the inverse, that's just not inverse proportional, it's inverse by the square, okay? So in other words, if you are twice as far away, you only have a quarter of the brightness. 3 times further away, 1/9 of the brightness, because it's an inverse square, not just an inverse proportionality, but by the square. And they have a pretty good little picture in the book. It's on my page 11. Is that on yours too? It's a concepts applied sort of in a tannish type block. Yeah. Inverse square relationships. You'll see there, and I'll just get you to imagine this. When you go out a little way from, say, a light source, a little way, all that light is in that square. You go twice as far, and that has spread. You can get 4 of those squares. Even if you're only twice as far, it spreads by 4. 3 times as far, it spreads by 9 times. So that's why it's inverse square law. Lots of things fall off by inverse square laws. Light, sound intensity, and basically braking speeds. You double your speed on the highway, 4 times the distance to stop. Triple your speed, 9 times the distance to stop. It's not a direct relationship there. It's inverse, and it's by the square. So that's why when you're moving at a faster rate, you stay even further behind. Otherwise, if something happens there, no way you're going to be able to stop in time. That's why tailgating, except a football game, not a good idea. Okay. I didn't say that there. Okay. Now, they have a blurb in the book, and it was in the title, the earlier stuff, but they didn't do any slides on it on how to solve the problems. So basically, we just practice this. I'll read you through. If you've had math or things, you've probably seen these before. Step 1, read through the problem, and they say make a list of the variables with their symbols, and they say on the left side of the page, and the unknown, Okay, I don't care where you put it, but notice we did that. As I read the problem, I wrote down volume, math, and I wrote down what we were looking for, okay? After I wrote down what we were looking for, then I asked y'all, what's the formula that relates what we're looking for and what we know? And if it's one like this, zap, you write it down, then do the math. Now, okay. So that's the step 1. Read through the problems, making a list as you go. both of what they've given and what you're looking for. Okay. Step 2, inspect the list of variables. We already went over that. Okay, and then write the equation that relates what you're looking for to what you know. Now, I was hoping this problem with the rock, they were going to switch it around. They didn't. It was exactly the same as the other two. But what if they had said, here is the density of the rock, here's the mass of the rock, what's its volume? Well, you use that same formula, but now you're looking for V. So you either rearrange the formula so it gives it to you, or you plug and chug or chug and plug, either way you want to. Okay? So write the equation down, and then, if necessary, solve the equation. Now, they like to tell you, and you can do it either way you want to, solve the equation for what you're looking for, and then plug in the numbers, or you can plug in the numbers and then solve what's missing. You can do it either way you want to. They're going to insist you do it one way. Okay, I was just going to suggest that, but I didn't know if you had run into it before or not. I'm going to clear this out of the way. I think I've used it about as much as I can. Now, is this what you're suggesting? Here we had rho. Goodness, let me start this over. That's really ugly. I've seen it done two ways. Okay. The what? Just like Ohm's law. Rho equal mass. No, I did it wrong. Yeah. Goodness gracious. I finally got my thing right and then started putting the letters in the wrong place. Okay. Here's the formula we just had. Rho equal mass per unit volume. So be sure you get it that way. Put rho here, mass is on top, volume's down here. Just like Ohm's law. Whatever it is that multiplies together to give you that, the multiplication's down here. Y'all seen this too or not? Yeah, okay. Yeah. You use it. You can use it anytime you have a 3-parameter problem that's related by multiplication or division. The thing that when you multiply together gives you the top, or whatever's on the top here, put here, and then rows here. So if you're looking for density, density is mass divided by volume. That's a dividing line, this is a multiplication line. If you're looking for volume, it's mass divided by density. If you're looking for mass, it's density multiplied by volume. And the other thing, folks, your units, if you keep up with your units, they let you know whether you're doing right too. Now, I've seen it in triangles. I've also seen people use circles. I kind of like triangles better, but circles will work just as well. Split that in half and split this one in half. Make this a multiplication, mass, rho, volume. Okay? Either way will work. And then later, when you have speed equal distance and time, Ohm's law, your power formula, just tons of things will work really nicely with this. So use it if you need it. Okay, that was outside of this. Solve the equation. But if you use these things, you don't have to do too much. Now, their step 4, I think, should have been much earlier. If necessary, convert unlike units. And I've already erased it, but when I was writing things down, I wrote down the units too. And if you saw something that was in grams per cubic centimeter here, but then over here you had inches on the side, whoa, can't do that. Get to one unit or the other, okay? Convert one way or another. Be sure everything is in the same unit. We'll see problems like that too. We'll get to it. Number 5, substitute the number value in for the symbols, okay? So you could have already done that, or you could wait till now to do it. Do the mathematical operations, pull out your calculator and do it. But in step 7, ask yourself if the number seems reasonable, okay? I give this example sometimes in math classes. Before I started teaching here, I was working at Southern Research Institute, and then we had something happen. We were funded mostly through EPA, and the Congress changed and all the EPA's extramural fundings got cut. So our program, we were on the radon program, it got cut because we didn't have any more funds. So we all were let go. Everybody in the radon group, there was about 6 of us. And so we were out looking for other work. And I started working at Jeff State as an adjunct instructor. And I was teaching Math 090, I think. I don't think I even taught any 098, just Math 090. And I remember there was one time, there was this one problem, homework problem, I think it was. Someone went into the store to buy 3 boxes of cookies. Each box contained 48 cookies, and they were $1.19 a box. How much did they pay for it? Well, most of the students, I'll admit, got it right, okay? But a few of them had it fractions of a penny, and a few of them had hundreds of dollars, okay? Because 48 was in the problem, wasn't it? You got to do something with it, either multiply by it or divide by it. Well, really, it was extraneous data. You didn't need it. 3 boxes of cookies, $1.19 a box, that's all you needed. Didn't matter how many cookies were in the box. But they used it because you don't want to waste a number, do you? Okay? Well, my question was, does this make sense? Okay? And of course it didn't. How could a box of cookies, 3 boxes of cookies cost less than 1 box? It couldn't. Or, if it cost $345, I wouldn't buy them, okay? Yeah, okay. Not those cookies anyway. Okay, so, no. Always ask yourself, does the answer make sense? If it's wacko, go back and check it out and see if you got something wrong. And not just that. Make sure the units make sense. That was back in step 4, but always keep up with the units. And if your units don't come out right, you're doing something wrong. Okay? You got a letter in the wrong place or somewhere. And then there's step 8. I find this looter. Draw a box around your answer. I don't care if you draw a box. Just make sure you have it. If you can help me see it, that's great. Okay? Here's an example problem they do. They had in the previous section, they had this. They were talking about proportionality constant. And what they had was a fuel pump. And the equation for the fuel pump, let me go on and clear this out of the way. Okay. Equation for the fuel pump is the volume of fuel is equal to the time over which you've been pumping multiplied by the constant, right? The longer you pump, the more fuel you get, right? The greater volume you got. And K would be your proportionality constant, okay? Then they gave you this. Suppose the flow rate, which is your K, was 40 liters per minute, okay? Then the volume would be T times 40 liters per minute. Now, of course, if you look at this carefully, you'll see T must be in minutes and volume will be in liters, okay? And that's what they use, okay? Now, they say use that same problem here, same procedure, and it says, same formula, this one right here, okay, where K is your flow rate. Okay, most pumps will have what their flow rate is on it. Okay, to predict how long it will take to fill an empty 80-liter tank. It says assume this flow rate, not 40, but we'll assume this flow rate is 80 liters per minute. Okay? For this problem, we'll do that one. Oh, I'm sorry. I read it wrong. That was 40. Sorry about that. It's the tank that's 80. Okay, sorry. This is 80, 40. The tank, the volume of the tank is the 80. Okay, sorry. 40 liters per minute is the K. The tank here is 80 liters. Okay? How long? What are we looking for there? Now, that's one question that could be in some circumstances a little ambiguous, right? If someone says, how long, what kind of answer you expect to give them? Time or length. And this problem is time, obviously. So that's your T. So this is what you're looking for. This was given and that was given. So now the way they set it up, they say solve this equation for T. Now if you're going to use your triangle or your circle, okay, then the V goes up here, the T here, and the K there, okay? And if you're looking for time, time is equal to V over K, okay? Or you can divide both sides by K, and the K's go out, and you have T is equal to V over K. However you do that. The volume of the tank is what? 80 liters. This is so simple, but I did want to show it for one reason. And what was your flow rate? 40 liters per minute. The reason I wanted to show this is watch how you do units. Okay, real easy to do the division there. What's that? Okay, the liters cancel out. That would be 2, but your units that you have here is 1 over 1 over minute. 1 over 1 over minute, because the others canceled out. Well, how do you figure out what that answer is? Remember how you do division of fractions? You could write this as 1 divided by 1 over a minute. How do you divide fractions? Flip and multiply. 1 times minute over 1. So your answer will be in minutes. And that sure it does make sense. That's a good time measurement. So, sure, 2 minutes. Okay. Then they go through these steps again, I swear. All right, here's another example problem. Let's clear these out of the way and do, because you are going to have some problems on your test. I do want you used to doing problems. Mercury is a liquid metal, someone said that exact phrase before, with a mass density. What symbol do we use for mass density? Rho. Okay, rho is equal to 13.6. We saw that in the table. That was in grams per cubic centimeter. Be sure you hang on to your units. What is the mass? So we're looking for mass, that's the unknown, of a 10.0 cubic centimeters of mercury. Okay, what's that 10.0 cubic centimeters? That's volume. Your units are your friends here. Pay attention to them. That's your volume for the mercury. So how are we going to solve this problem? Say that again. You multiply. Remember, mass was on top, and rho and volume were on the bottom. So you're looking for mass. If it's a triangle here, you multiply those two. And what's more, your units are your friends. They tell you this is rho times volume. Look at the units. 13.6 grams per cubic centimeter. It's a pain to write them down, but look at what it does for you. Times 10.0 cubic centimeters. And sure enough, the cubic centimeters cancel out, and you're left with what? And how much? A little louder? And 13.6 times 10, and that gives you 136 grams. There's your answer with the units all just like you want. That answers the question. Mass in grams, perfect. Okay? All right. Have we beat that to death yet? Okay. What's that? Yeah.
How do you spell rho?
How is it spelled? Rather strange. R-H-O. Rho. Yeah, it's Greek. Exactly. Not an English word. Okay. Now we'll see some words sort of like this later in the text, and we'll, especially in the electricity chapter, you'll run into a word that almost reminds you of that one, but it was a little different. All right, so now we're ready. Okay, let's get through all this stuff. We already hit that. Okay, now we're picking up on page 13. This is where we're supposed to pick up the nature of science. Is this anything close to right? Science began only about 300 years ago. Well, science has always been here. It's just that our understanding of science, the way we understand science, has only been around about 300 years. Now, sure, way back, the Greeks, they were smart people, really smart people. And they observed nature. And they suggested things. Okay? Aristotle is infamous or famous for doing this. And he was such a bright guy that for literally thousands of years, if Aristotle said it way back then, they still believed it. Because he was one bright dude. Okay? But what Aristotle didn't do was test his suggestions. It was only about 300 years ago that a guy named Galileo, Italian guy, decided to question some of the things that Aristotle, everybody had believed. Now, Galileo was what? I don't remember, 1400s or something like that. Aristotle had been like BC, 400 BC, so it had been close to 2,000 years. People had just been, sure, yeah, Aristotle said it, we believe it, okay? But Galileo came up with something new, testing to see if those assumptions or suggestions were right. The year that Galileo died, Newton was born up in England. They never interacted, except if they tag teamed on the way out, I don't know. But anyway, Newton came along. He built on what Galileo said. The ancient natural philosophers, like Aristotle, but many others, they did it by thinking only. The additional component that Galileo and Newton did was they experimented, okay? Experimental evidence. They tested things. They said, well, if this is true, then this should work. And they would try it. If it didn't work, why didn't it work? Tried something else, and they came up with some that's when really science began. Just thinking about it, you think that would be enough for science. No, you have to do a little bit more. So basically what Galileo and later Newton and many others built on this was what is called the scientific method. Starts with observing some aspect of nature. The Greeks did this big time. They did a great job of observing. Okay? Propose an explanation for something observed. They did it really well, and many of theirs were fine. They were perfectly good. Okay? Even to the point of using the explanation, not really. This is where they fell apart. They proposed explanations, and because they did, and people said, those are smart people, we'll believe them. But they didn't make predictions and then test those. Here's the big step. Testing the predictions with experiments and more observations. And if they work, try something else. If they didn't work, change something. Modify the explanation as necessary. If something didn't work well, try it again. Okay? Make another prediction. Try another experiment. Return to 3. Okay? And go through the loop over and over again. And many things for instance, Isaac Newton is well known for his law of gravitation, his 3 laws of motion, all these kinds of things. Guess what? About 300 years later after him, a little old guy named Einstein came along and said, these don't quite work always, do they? It wasn't just Einstein, several others. And we found out, no, they don't on certain levels. Maybe they worked fine on the macro level, but they didn't work fine at the macroscopic level, okay? And that's when quantum mechanics and things like this came into play. And actually gravity, Einstein came up with some really lofty ideas that were really hard to follow, and it's only been during your lifetime that some of those have been able to be tested, even though he died, 50s or 60s, I think, sometime around in there. They said, bright guy, we'll believe him, but we don't know if it works or not. Just recently have they proven some of his stuff. Yeah.
You know, people talk about Galileo and
Yeah.
Isaac and Einstein. Do we have anybody like that around alive today that is well known for something other than researching in today's medicine?
Yeah. Probably a lot of times the brilliance isn't realized until after they're dead, you know. But yeah, there are some. Say again?
Probably top secret information.
Yeah, some of it might be. For instance, goodness, I'm going blank on his name. He has ALS. Stephen Hawking. He has done some incredible work. I think he's still alive too, isn't he? What's that?
I said he took like Einstein's idea to like a whole next level.
Yeah, and so and I mean he's strapped in a wheelchair. He has Lou Gehrig's disease. It's really ALS. He can't even talk. You know, he has a computer-aided voice. You know, but he's one bright dude. So he's doing some things, and there's many others. And like you say, we may not know about all of them now.
Government probably gathering
The Defense Department has a lot of things going that we might see. For instance, any of you use GPS?
Yeah.
How long have you used that, or your folks used it? Not really been that common for more than about 10, 12 years, 15 years.
It's been around longer
Huh?
than that.
It's been around a lot longer. When I was in the U.S. Navy in 73, 74, 75, sometime around in there, it was placed on the ships.
But still,
It was
what
called
we use-
satellite navigation
what
then.
we use is not as accurate as what
You better believe it's not. They could probably read I won't want to say, this is probably a slight exaggeration. If you had a newspaper in the back of your truck there, they could probably read it. Okay, our navigation isn't that precise, but you know, we can get within maybe 10 meters. They can get certainly within a meter, and maybe smaller than that. Yeah, we have the scaled down version. So yeah, there's lots of things happening like that.
You ever watch CSI?
What's that?
You ever watch CSI? Well, they can realize it's like 3
Yeah.
miles away on the camera.
What's the Will Smith movie where they was following him around with satellites? Gene Hackman was in it.
Yeah, I remember the movie, but I don't remember its name.
Enemy of the state.
Yeah.
Enemy of the State, right? Okay.
Someone out there, Ryan.
Okay. So the scientific method, this basically is a quick outline of it. Okay? Here's an example. Now, and this keeps, in a sense, evolving. Okay? What are atoms made of? Now, believe it or not, the word atom was coined by one of those really smart Greek guys back probably 100 or 200 years before Aristotle. He just did a thought experiment. That's what they call it. That's what we call them now. They didn't. He just thought, what if I had a bar of iron here and broke it into two? Now I have 2 bars of iron. And then let's break this and you have the smaller bars of iron. What if I just kept breaking the smallest one and kept breaking and breaking and breaking? Is there some place where I can't break it anymore and I have the smallest piece of iron that I could possibly have? And even though he couldn't do it, he thought through it and said, yeah, there's got to be. So he called that smallest piece of whatever, iron, copper, whatever it was, he called it indivisible. That's where the Greek word for atom. That's where our word for atom comes from, the Greek word indivisible. The smallest particle you can get without being invisible. But then a couple hundred years later, here came Aristotle. And he said, no, I don't believe this. That guy's name was Democritus, by the way. And Aristotle said, no, matter is a continuum. You can't get a smallest piece. No matter how small, you can still break it. It's just a continuum. It exists and always exists. Yeah. So he threw out, and people didn't believe it anymore. Well, one of Aristotle's other concepts was all matter is made up of 4 basic elements: earth, wind, water, and fire. 3 out of those made a singing group, right? Never mind. Okay, no. Okay. And so he said, that's it. Everything else is made out of earth, wind, water, or fire. Okay? And when the scientific revolution came around, they were still believing that, and they said, hey, earth is cheap, water is cheap, wind is cheap, fire is cheap. If that's true, then I should be able to combine various combinations of earth, wind, water, and fire together and come up with gold. And I can make me some money. That's when, or other precious metals. So they started doing it. They started testing, mixing, grinding, heating, diluting, doing all sorts of things to it. And as they did this, you know what they were doing? They were called alchemists. That was called alchemistry. And later that became chemistry, okay? They didn't know what chemistry were. They were doing early chemistry experiments. Now, they found after a while they had to start writing things down because they didn't want to do the same thing twice. So they would write down and measure and be very careful and precise in their measurements. In fact, Isaac Newton was one of these alchemists, and doing this. And they found out, hey, here's a substance we didn't know was there before. And after a while they said, this can't be true. We're finding a lot more materials that we can't break down into anything else. So basically, that was the beginning of what we consider the atomic. They started thinking back. So what are atoms made of? Well, we know today, and they sure didn't know it back then, they're made out of a positive nucleus, and that's really tiny, incredibly tiny, okay? Surrounded by these negative electrons, okay, floating all over the place, okay? All the mass was pretty much in the nucleus. Those electrons had some mass, but barely anything, like 1/10,000th of the mass of one piece of that nucleus, okay? They were just incredibly light. So negative electrons orbiting positive nuclei. What they did, they started colliding atoms, and they produced free electrons. That's how they tested and found out, yeah, that's what they are, We didn't know that. Atoms really are divisible. You can break off some electrons sometimes. Colliding 2 atoms yielded electrons, protons, and neutrons. Now, what's the difference? Electrons, protons, and neutrons. Okay, electrons are negative, protons are positive, and neutrons are neutral. They don't have any charge. But almost all the mass of an atom is in the protons and neutrons, and they're all in the nucleus. And the electrons having any mass, hardly any mass at all, are taking up most of the volume of that atom. Okay, this was all found out through experimentation. And I can remember my older brother coming home from college after the first time he took physics, and he said, all of everything is nothing. And what he meant was that all the mass is in this tiny little speck in the middle, and the electrons are floating around it. They have a little bit of mass, but not very much. And then most of the space in there was as void as outer space. Most of everything is nothing. Okay? Atoms are made of electrons orbiting the nuclei, made up of protons and neutrons. Collide them at higher and higher energies, and guess what? You can find all sorts of things there. So this is basically the scientific method at work. Okay? Okay, if you collide the right or wrong things, yes, you can. In fact, the 2 types of nuclear bombs, okay, atomic bombs. The first of these is when you take a really heavy atom, think uranium, plutonium, one of those, that's already somewhat unstable, and bomb it with more neutrons. Expose it to a lot of neutrons. What's that?
How would you expose it to a bunch of neutrons?
Well, there are things that give off neutrons, radioactive material that gives off neutrons, and put them in, well, actually, if you have enough of pretty pure uranium or plutonium or whatever it is, and you have enough and put it closer, they give off radiation because they're radioactive. And part of that radiation is additional neutrons, okay? And if they hit each other and you get enough of them in what they call a critical mass, then you have an explosion. So what the original, and this is called a fission reaction, okay? And this is what the first atomic bomb was, okay? They had a little bit more than half the mass here, a little bit more than half the mass here, and at a certain time, after they dropped the bomb, they had explosives around those, and when they dropped the bomb from way up high, they had some sort of way of detonating, so they tried to detonate it so that the explosives push those two half masses together, and before it hit, and when they did, you had a nuclear explosion. So actually, the nuclear explosion, the first flash you see is that conventional explosives pushing those together. Then you don't see anything else. Okay, so no one's ever talked about that. Then is in the nuclear reaction. So that's a fission reaction because what you're doing, the neutrons are making those heavy atoms unstable, and they split. Okay, that's why it's called fission. Now, to make a fusion reaction, that's what's going on in the sun continuously, and every star that's burning bright out there. That's what's happening, because then what you have, hydrogen atoms, the lightest, the smallest atoms possible, colliding with such force that they form helium atoms, and that's called fusion. Now, we have had some fusion hydrogen bombs, you may have heard that, way more destructive than uranium plutonium fission bombs. In fact, the only way we have so far of getting a hydrogen enough energy to force those together to make them explode is to have a fission bomb around them that you set off, and it has enough energy to force those together, and then they explode. So you have the conventional bomb forcing together the fissional material, and then that forces together the fusion material, and then you have a big explosion, a huge explosion. And that's happening on the sun naturally, because it's so high of energy. So yeah, you can make that happen, but it's really hard to do, thank goodness. Okay. Okay, yeah. And
when you would pour hot metal on top of a wet any kind of water.
I'll say that again.
They would be filling up these pots, and these pots have water in them,
Yeah.
moisture. When they pour that hot steel on it, it would create a hydrogen bomb in there. It could blow up a whole train car in pieces.
Okay, I think I know what you're talking about there. Actually, what's happening there, you're burning hydrogen. That's not a hydrogen bomb. It's an explosion for sure.
Oxygen in there making it burn hotter.
Okay, do we hear? Does anyone know what a Zeppelin was? I know Led Zeppelin's another group. But tell you, huh? A blimp. What the earliest blimp?
They use hydrogen back then.
They used hydrogen. Okay, because it's the lightest gas, and that was the first aircraft before they knew how to fly planes. They had blimps. Okay, and the blimps used hydrogen because it's the lightest gas. It would lift them easier. The problem is, it's a Hindenburg. Okay, was the name of this one that happened over Germany, I think somewhere. It either flew during an electrical storm and got struck by lightning, or it hit something and tore the skin with enough friction that had heat. And hydrogen burns really hot, okay? And so that, I think, is probably what happened. The pouring steel into water, you probably actually ionized hydrogen, and then when the hydrogen combined back with oxygen at very high temperature, it's going to burn and burn. Yeah, you can blow up things really easily. Wasn't quite a hydrogen bomb, but it was still a very hot explosion. Now, I don't know for sure. That's my guess. Okay. So, general scientific activities: collect observations, develop explanations, test the explanations. The Greeks did real good at this and pretty good at that. They just didn't test. This is what Galileo, Newton, and many others since then have added to the picture. And that's when they say science began, when you started testing. There's a little blurb at the top of page 15 when you get your books, and it's on basic and applied research. Okay? And some of the things y'all have been talking about here, some of that is basic and some is applied. For instance, basic research would be looking into ways to harness. Okay, let's back off a minute. What's the problem with burning fossil fuels? That's what we use most of the time.
It can put off chemicals.
Second?
It can put off chemicals.
Okay. Any idea what chemicals? Huh?
Harmful carbon monoxide.
Okay. Carbon monoxide is deadly. Carbon dioxide, a lot of that is put off, and they think that may be contributing to global warming. All fossil fuels, coal worse than others, have sulfur in them. Sulfur dioxide is pretty bad because when it mixes with water, it's sulfuric acid, and that can kill plants, damage other things, and also is harmful to breathe. You have pollutants, you have the ash, you have things. There's lots of negative things. Okay? How about hydrogen? What happens when you burn hydrogen? What's the byproduct?
Hydrocarbon.
Hydrogen plus oxygen. Water. That is a real... Water is not too bad, right? It's not a bad thing at all. It's a chemical, but it's not a bad chemical. In fact, it's a pretty good chemical to have around. So, yeah, why don't we burn more hydrogen? Well, hydrogen's really hard to get a hold of. It's really hard to store. It's really hard to send through tubes or pipes and stuff because hydrogen atoms are so small. They go right through the rubber or the neoprene or the joints and things, and it's explosive, so you don't want it leaking out and under high pressure. I mean, it has some problems, but it's a much cleaner burning fuel. Your byproduct is water. So yeah, there's some give and take. So a lot of basic research may be on how to actually harness hydrogen, how to extract it, things like this. Applied research would then be, once you've got something in hand, how can you best use it? One of the things, I believe Einstein's responsible for this one. No, actually it may have been a couple of other guys. The photoelectric effect. Someone noticed or did a lot of work and saw that sunlight, if it hits the right material at the right angles and the right films and stuff like this over it, it actually can be used to produce electrical charge. Okay? Basic research. Applied research. Now, I'm going to calculate some more. Okay. Any? Oh, that's not the right one. Okay. Ah! You got one.
It's the same one.
What is it? Oh, okay.
Well,
No, his is different, okay? You know what this is? Is the thing across the top? Yeah, it's a photopath. It used the photoelectric effect that someone did back in basic research, found out it happened, someone applied that, and powers this calculator. That's what's called the solar does after you solar to be incoming light. So yeah, there's basic research, someone figuring out a way to use that. Second? Yeah. Oh, he has another calculator that has it. Okay, good deal. Okay. So, let's look at how we go about doing this. Now, you mentioned medical. My wife's a researcher at UAB, actually, She works for UAB, but works in Children's Hospital. She does pediatric research. And they do this kind of stuff all the time. Hypothesis. You come up with an idea. That's a recommended thesis. You know, you think this may be true. Tentative explanation for some observation. Why is this happening? Well, could it be this? Okay? Tentative explanation for an observation. Come up with experiments that test those things. Recreate the event, that's not recreate, but recreate the event or occurrence to test that hypothesis. Okay? She works mostly, most of her research has been on a virus. It's a herpes virus called cytomegalovirus. Any of you ever heard of that? Most people haven't. One of the most common viruses out there. If you or I were to be exposed to it, you probably already have been, but if you haven't been and were exposed to it, you might feel like you have a mild cold, or at worst, a really mild case of the flu. Be over in a couple days, you never think about it again. And then you got the antibodies and stuff, you never would get it. You could get exposed again, you probably never get it. No harm, no foul, right? Unless, and this wouldn't happen to any of you, but if you were a woman who happened to be pregnant when you were first exposed to the virus, then it wouldn't bother you any. You might feel like you had a mild cold or flu or something, no sweat. But you transmit that virus to the baby in utero, and the baby could have absolutely no problems. It could have mild, what they call sequelae, or it could have pretty serious ones, or it could have death. I'm hard of hearing, and one of the most common side effects for a child, for an infant, fetus to be exposed, is the child is born with loss of hearing. And Karen swears I must have had that as a child, you know, because I'm really bad at it. But it could have been caused by other things too. But she has spent most of her career studying that virus, what transmits, you know, and things, and they do these kind of things all the time. They come up with experiments they do controlled experiments. When she was doing one of her studies for her doctorate, she was doing that because she had me helping with the data, with looking through. They would determine if a woman was born, if the newborn had CMV. If it did, then she went back and studied the mother to see maybe how the mother contracted when she had it. They looked at her blood work and stuff. So they were studying those cases. Those were called the cases, experimental group. But then for every one that had it, they try to find at least two that didn't have it. So they looked at babies that were born the same day or within a day or two, same gender, same racial, same socioeconomic strata. They try to get as many things as the same. They call that the control group. This is a controlled experiment, comparing two situations with as many factors as possible, identical, except the one. One was CMV positive and one was CMV negative. So they would do this, and she collected these, as many as she could, over however long a time she had to do it, and then look at some of the factors. And what she found on the first thing, sexually transmitted diseases were far more likely to have shown up with the case groups than with control. So the odds are those women were much more sexually active. So good indication it was a sexually transmitted disease. Now, it didn't have to be. Others, yeah, and they went through and over the years have got more and more information about it. But this is what you call a controlled experiment. When I was in grad school at University of Georgia, I was in agricultural area, we'd go out and do plots of land, okay? We'd take soil samples from all the plots. You know, we had it split up. We put a certain fertilization scheme on each plot, but we changed one and only one feature, like maybe liming, okay? So we'd have the same potassium, same nitrogen, same calcium, same sulfur, same potash, same everything, except the liming levels would be different. And then we saw what kind of results you got from that. That was a controlled experiment. You try to keep all the factors exactly alike except the one you're trying to test. That's how you investigate. That's how science basically works. Okay? This guy, the author here, is a little bit over the board with pseudoscience. But is this something to be concerned with? Anyone know what that means? What's the prefix pseudo mean? Okay. In other words, false. It's a false name. A pseudonym is a false name. Like, pretty famous author. She was a woman, but she published all her books under a man's name because he didn't think women could write. And she got to be a really famous. We got to meet this guy, because I can't think of what name she used. And then after she was extraordinarily successful, then she revealed that she was actually a woman. Whoops. Okay, she can write, But that was a pseudonym. She went under a false name. This is false science. Misleading or often absurd claims of scientific results. This is remember when I talked about the research paper and warned you about the internet? Too much of that out there. So how do we test it? See if this science that you're reading about has had academic and scientific background of the claimant. Who is proposing this stuff? Now, sometimes some people can find some things without having a lot of real good things behind them, but most of the time you basically have to have a lot of training to hit this science at the levels we've been talking about. The history of review by scientific peers. Boy, this is such a pain for the scientists. Karen writes all the time about it. You do all this work, put in all this thing, write these papers, they send it out for review, and some people are out there just trying to rip it to shreds, A lot of times she feels like it's because they wish they had thought of it first, So they gripe and complain and stuff, and it's really painful, but you have to have it to make sure the science is right. Participating in scientific institutions, organizations, meetings where you hash it out, talk it over, and things. Got to have that. And the claims published, again, in peer-reviewed journals, independently validated by others. They actually pay people. When you write up a paper, you have to put the materials, the methods, every step of the way, and they'll actually fund research for someone else. We want you to do this way. And you go and do it. You don't know why. You get the funding for it, you do it, and then you give them the results. If you don't get the same results as this, something is wrong, and they make the original authors explain why this couldn't be. And they've actually found some intentional fraud. They've also found some places where people just made errors. But they need to know both of them. And unfortunately, some of the top schools, I think Stanford University in California, Harvard, some of the big name schools, Duke, they've had occasionally, not often, occasionally things. Well, what happens? They put the people's hiring status based on whether they produce results. And you do spend years and years and years putting things together, and you come this close but not quite, and they'll fudge a little bit because they don't want to get fired. They want to stay around long enough to find out whether what they're working on really does, but they just didn't quite get there yet, so they'll fudge it a little bit, make it sound like they got something they really don't. That's why it takes drugs so long to get through the pipeline. They've got to make sure they really do what they say and don't have any negative side effects. That's what he's talking suicide.
All of them now have negative side effects.
What's that?
All of them now have negative side effects.
Yeah, I know. Boy, you hear those commercials? You hear about the drug, and then they say, but don't take it, it sounds like an auctioneer talking of things that if this happens, then stop. If this, yeah, they all have.
They might put it on that fine.
Oh, in really small print,
So
yeah.
they can say, we did put that.
Yeah, we put it out there. You can't sue us. Yeah, everything's driven by litigation these days. That's disgusting.
That's how the press is going to cause you to have uncontrollable diarrhea. And, I'm just real big press.
Yeah.
But no one's going to be happy after that.
You get the blue pill, it helps one thing and make you go blind.
Yeah. I didn't say this at the beginning of the term. I probably should have. when I was talking about office hours and stuff, I have a mild form of leukemia, okay? So I have to go in for treatment every 2 months. And it's a pretty good drug. It doesn't have nearly as many side effects as I don't know how many years ago it was. I had pretty heavy-duty chemo on it. But, you know, no sweat there. But now this one, even though it's pretty low side effect, they have to give me 2 types of steroids, Benadryl, Tylenol, all before they can even start the drug, because the drug. Any of you know anyone with peanut allergies? Okay.
My brother had it took the child.
Yeah.
I don't know what.
Okay. This drug that they give me, the actual drug, and it's just a tiny amount that they give me. I have to do all this ahead of time, and it still takes 4 hours for them to administer the drug because they do it at such a slow rate. It was developed in rats, and most people's bodies don't like having that material in them. So they give you all this stuff to keep the side effects down, and still 3 out of 4 times when I've had the drug, I'll break out in a rash about in the middle of the drug, and then they have to stop it and give me more steroid or something else till the rash goes away, and then start it again. So yeah, it's all over the place. Now, that's not bad. By the time it's over with, it's gone, and I work the next day. There's no problem. But usually I have those treatments on Friday, so I don't miss any classes, so y'all don't have to worry. But my doctor only sees patients on Tuesday morning, so I have to miss every 2 months. I have to miss either a math class or some sort of class because I have that. But it won't affect this one any because it's in the morning, not in the afternoon. So y'all don't have to worry. Okay. Now let's look at laws and principles. This is how science is sort of organized. There are certain things called laws. These are important relationships observed to occur time after time after time. You throw a ball into the air, it's always going to fall back to the ground. That's the law of gravity. It's a law. It always works, okay? It's usually descriptive in nature, though it can have, and here's an example, your law. Remember it? No, I'm just kidding. This guy's last name was Charles. Charles's law, relationship between temperature and pressure in a gas. Y'all know this? Basically? Just as an example, when I was living in Lincoln, Lincoln, Nebraska, that's where I was doing my graduate work. Yeah. Well, yeah. That's sort of a thing. There was this kid in the church. His father had divorced his mom and moved to another part of the state. He was a young preteen, and she thought he needed some male influence, not just her influence all the time. She was begging people, guys in the church. Well, I didn't have any kids, so I said, no interest of mine, But then when he came out and was playing on the church softball team, he was a really good athlete. And because he was so young, he was a little shy around the guys. And I just tried to make him feel at ease. I was catching, and he was a third baseman. So we just hit it off well. So I thought, well, maybe I can do some stuff with him. So we did, and I'd go over maybe on Sunday afternoon. Nebraska can get pretty cold. And one Saturday, he had left the basketball outside. And it was still pretty cold Sunday afternoon when I got there, picked it up. He said, oh, the basketball went flat. And like I said, it was pretty cold out. I said, no, take it inside, leave it there for a while. Don't pump it up yet. He thought I was sort of nuts. And we did something else, messed around some. I said, how about going and get your basketball? He did. It wasn't flat anymore. Why? Because of the relationship between the temperature and the pressure in gases. You increase the temperature, the pressure increases. When do you check your tire pressure in the car? Right after you've been on the interstate driving for about 3 hours in the summertime, hot asphalt, is that when you should check your pressure in the tire? No. It's going to be really high then, right? Okay, you wait until it's pretty cool, you haven't driven it far. That's when you check it, okay? Relationship between temperature, that's Charles. It happens every time, Okay? That's a law. Now, principles are very similar, very similar. They're also descriptive in nature, but they're a little more specific. Notice all the weasel words, a little more specific. You know, it's hard to tell which is the law, which is it. The difference is largely one of extent. Some people may call one thing a law, they say, no, that's a principle. Who cares? But it's not always a clear distinction. Here's one. Archimedes' principle, or someone could call it the law of flotation, whichever. It relates objects, fluids, buoyancy, and that kind of stuff. That's generally a principle, most people would say, but others say, oh, no, that always happens, it's a law. Who cares what you call it? But you kind of divide them up this way. If you have a little more data on it, you're a little more specific, call it a principle. Okay? How did you get there? Well, you got there by having theories. Remember we mentioned hypothesis? That's the first general idea. Well, you test that and you say, you know, it looks like this happens most of the time. After a while, broadly based set of working hypotheses. You put all these together, yeah, this one works, that one works. Well, maybe this is what's going on here. It's based on considerable experimental support. And this forms the framework for more thoughts, more experimentation. Okay? That's what a theory is. Now, a model is a collection of theories, just like the theory is a collection of working hypotheses. This would be a collection of theories or ideas intended to represent a physical system. Okay? Quite often useful for regimes that are either too small, like how do you know what, here's a sort of a dumb example. Remember I was talking about the people, the alchemists, that putting together all these things and finding out they could mix things in certain ways and produce other things. They noticed after a while they got off of looking for gold and that kind of stuff. Oh, did I like it? I'm sorry. It's just a force of habit. Okay. Thank you. Okay. They noticed over time that they came up with this sort of a law back there, and they said the law of definite proportions. If you combine this much with this much of these materials, you're always going to get this much of that. And of course, the sum had to work out. If you had excess of this or a deficit of that, you're not going to make as much. If you had excess of this and not enough of that, it always goes by this definite proportion. Well, British or Scottish guy named John Dalton, after studying many of these things, he thought, hey, it looks like, and this was his model, and he knew it wasn't actually what happened, but he had this idea, consider oxygen. Oxygen looks like it always combines in twos. So let's say oxygen has two hooks on it. Hydrogen always combines by one, so it has one hook. So what would you expect? One oxygen with two hooks, two hydrogen, one hook each. What you got? H2O. Carbon has four hooks, and hydrogen one hook. CH4 is methane. Yeah, okay? And then other things like carbon two hooks, carbon four hooks, oxygen two hooks, CO2. Yeah, they always combine at certain ratios. Now, he pretty much knew they didn't have hooks on it, but that was his model to describe. It's just a representation. And you can't tell what's happening down on that level. You can't see those carbon atoms. Sure can't see any hooks on them. You can't see oxygen atoms, but he knew they always combined in those ratios. It can be physical, like he was describing. It can also be mathematical. There was another guy named, I know he was Scottish. What was his name? Did you like that? Yes, sir. Okay, good. His name was James Clerk, spelled Clerk, but it was pronounced Clerk Maxwell. He had been studying, they knew for a long time there's some connection between electricity and magnetism. It's sort of obvious there is. No one knew what it was. And James Clerk Maxwell came up with mathematically 4 really complicated looking equations, but they all made sense to him. They were all internally consistent. And he said, I think this may do it. And it fit mathematically, but we didn't. This was way before we had the technology to test them. And it seems like it was something like 70 years after his death, they finally were able to test them, and lo and behold, Maxwell's equations fit like a champ. Nothing to be changed in them. His was a mathematical model that explained the stuff, but we couldn't tell it for sure until much later. There was another guy named Avogadro. He looked at some of these ways that things put together, especially gases. Now, the law of definite proportions, that made sense, but when they looked at gases combining, they found out if you had 3 quantities, okay, let's say liters of hydrogen, 3 liters of hydrogen combining with 1 liter of nitrogen, yeah. 3 liters of hydrogen, 1 liter of nitrogen. What do you think you would get out of it? 4 liters of ammonia? No, I only came out with 1 liter of ammonia. What happened to the other 2 liters? Well, it's just the way they combine. So, and there was real puzzlement. You know, they couldn't figure it out. And this guy named Avogadro, which I think was Italian too, I'm not sure, he said, well, what if a liter of gas at a standard temperature and pressure contains only a certain number of molecules? No matter how big or how small those molecules, they all contain the same number of molecules. They said, are you nuts? Why would that be? What basis would you have of that? Nah, get out of here. He died years before the rest of the scientific community, who made so much fun of him, said, you know, he was right. You know, he had a model that fit, but no one believed it until way after his death and said, you know, Avogadro, we made fun of him, we kicked him out of our organization. I don't know if they did that, but you know, and he turned out being right. Well, here's a situation. I don't know if you can see this well from where you're sitting. I don't know if you've seen one of these, but they're beautiful to behold. But certainly everybody's seen a rainbow. And occasionally you get to see a double rainbow. Now what do you notice about that, if you've ever seen one or just this picture of it?
It's a reflection.
Say again?
It's a reflection of it. Of the first one.
Okay, very good. Right. Even so down. Notice this is blue and violet and stuff on the inside and red and orange on the outside. But the outer one is red and orange on the inside and blue and green on the outside. The colors are reversed in exactly that order. What else do you notice about the two? The what? No.
One of them's darker.
Oh yeah, one of them's quite distinct and the other one's very pale. Do you ever see it the other way, that the white one's out here and the pale one inside? Never. Okay. So here's some observations about it. Reverse the colors and stuff. Why in the world would that be the case? Okay. Say again? Nope, not quite. The moisture, you got it. The little droplets of water in the air, they have to be the light. Okay, the lights, and here's something you probably can't tell from this picture. If you've ever seen a rainbow, and the next rainbow you see, notice. Do you ever see rainbows around the middle of the day, like noonish? Do you have seen one? No, not around noon. When do you usually see them? Evening, late afternoon. Maybe sometimes early morning. And here's why. Next rainbow you happen to see, look at the rainbow, look behind you, and you'll find the sun. The sun's always got to be behind you. You'll never see a rainbow on the same side of the sun. There's another clue. You've seen the clues about the brightness. You've seen the clues about the colors. If you had noticed, you'll notice the sun is always behind you. Always. And the sun, the rays of the sun is coming in parallel. Oh, this is wave theory. We're not going to get into it. Coming in parallel. Okay? Here's what the theory is. let's imagine those little drops of water, because it's always right after a rain. That's why it's called a rainbow, right? You know, there's moisture in the air, lots of moisture in the air, little droplets of water. Let's imagine that they are spherical drops. Pretty good guess. Most things will go to spheres if they can. If the sunlight's coming in at a given place here, and happens, if you hit the rainbow, if you hit the droplet of water here, the light goes right through. Okay? Maybe a little bit that is diffused. But if you happen to come in at just a certain place on that drop of water, and the sunlight's coming in, hitting lots of drops of water just at that place, then what you have is, this is called refraction. When you go from one medium, air, to another medium, water, water has a different index of refraction, so the light gets split. It's like a prism, okay? Light will separate into the colors. Violet, well, let's start here. Red, orange, yellow, blue, green, blue, indigo, and violet, okay? And it splits that way because of the different wavelengths of light, okay? Now, the reason that this angle here, light's hitting from all this place, but this place here, right at the back of the drop of water, you have what they call internal reflection, okay? It's at a certain angle is the angle you have total internal reflection. Can anyone think of a system that we have that uses this aspect of light? Fiber optics. That's why they call it optics. Fiber optic cable, really great stuff. You can get extraordinarily clear things from that. You actually have light that's going through and reflecting off the back of a certain material in there, and it's doing this kind of stuff all the way down the thing. That's what fiber optics is all about. Okay? All right. Anyway, that's a different story. So it reflects off the back of that droplet, and when it reflects, you tend to reverse the order, and then it comes out again, and what comes out is at a reverse. Well, the way they show it, it comes out kind of at a certain spectrum, okay? And the only way this is going to happen is if this angle between the incident ray and the external ray is 42 degrees. And if you were to find the center of that half circle that the rainbow is doing there, find its center and use a sextant and measure out, you find that's always 42 degrees. Always. Okay? But if that light, and it could have been up here or down here, they just flipped it over, came in right at the edge of that, right at the edge, then you get total internal reflection there, but rather than going out, you have a second total internal reflection that flips it again, and this is now twisted, that extra twist there reverses, and that's why you see the light in the reversed order. Okay? But this is also why the inner one is darker, because more light comes in through this part and that part of the droplet of water than goes through that part or that part. I mean, just a little bit of light does that, so this is a very weak light. That's why you don't see most of them. Most of the time you see a rainbow, there's always a second one out there, it's just too dim for you to see. But this is a very bright one here, so you do get to see that. So it's a combination of reflection off the back of the drop of water and refraction within the drop of water, and then you refract again when it comes out, but it's reversed the order. That's why you get it. And by the way, that angle is 51 degrees. So sure enough, that's always on the outside. The reversed color and the dimmer is always on the outside. That's the model that explains why you can see sometimes a double rainbow. Okay. Let's see. As I said, this guy goes a little bit overboard, I think, with pseudoscience. He has a concepts applied. Seekers of pseudoscience, okay? He mentioned things like psychics and forked sticks to find water, Bigfoot, Bermuda Triangle, all the things like this. I think he overdoes it a bit. Let me just see if there's anything else here. Oh, here was one. I don't think the book has this one. It doesn't. It's right at the end of the chapter. This is another time. Have y'all heard of the theory of continental drift? You ever heard of that? Moving apart, yeah. Yeah, in fact, we have a new name for it today. It's called plate tectonics, okay? And it's a very well-established theory, okay? And it explains a whole lot. But when this was first proposed, and it wasn't proposed out of earthquakes and things like this, it was proposed because someone looked at a globe and said, look at this. It looks like South America came out of the armpit of Africa. It looks like the bulge in Africa fit right up into the Gulf of Mexico and the Caribbean. It looks like the slope of the North America matches the slope, just in the opposite direction of Northern Europe. They said, look at that. You reckon these were ever the same? And geologists and others said, are you nuts? Continents don't move, they're fixed. How could they move, you know? Impossible for them to move. Yet today, we've discovered right down the middle of the Atlantic Ocean is a ridge. The reason there's a ridge, plates are separating there and just constantly volcanic eruptions out of that because the plates are moving apart, and that's what made the ridge. The magma has made its way to the surface, become lava, and that's why the ridge is down the middle of the Atlantic Ocean. So what was once considered nuts has now been validated with experimentation, measurements, data. Okay? And pretty incredible. All right, that does finish the chapter. Now, I say this, say again? Oh yeah, but let me finish saying what I'm going to here. I'm going to say this every stinking chapter, so get used to hearing it. But none of the chapters stink, by the way. Okay. Nothing replaces reading the chapters. I know most of you don't have your books yet, but when you get your books, please read the chapters. Okay? I said this over and over one time in one of these two courses I taught, and I had a guy who sat right over here somewhere, the desk faced this way back then. He was was here quite a bit, one of my better students, had pretty good scores. But I kept saying this every chapter, and he came in one time, more than halfway through the course, and boy, he aced the test. I mean, he had made good grades, but man, he aced this one. I said, yeah, did a good job on this. He said, yeah, that thing about reading the chapters really helps. I thought he'd been reading them all along because he was a pretty good student. And when he actually read it, I mean, he said, wow, this really makes a difference. So I'm not just kidding. It does make a difference. Once you've read the chapter, then there's a summary at the end of the chapter. And in the summary, it either, most of the time, italicizes words, occasionally maybe boldface or something like that. It's a good way to go through and pick out some of the high points. They don't get it all. You need to read the chapter to get that. Also here's a people behind the science. Here's one on Florence Bascom. I know y'all don't have the book, so I'll just hold it up. Nice little blurb here, well worth a read. I had never heard of the woman before I read this textbook, okay? She could be who you might choose to write your paper on. But remember this cannot be your source, okay? Even though you got more than enough material here, you have to get an outside source. Remember, your textbook cannot be a source. But hopefully you can get so interested in, hey, I want to find out more, and go find the source. You could write on her. And more than likely, they mentioned probably several other names here that may give you other people that you might look at. Right now I'm not seeing any, but I'm almost certain there are some others in here. There's a few ones I'm not seeing any right off the top. Well, here's a few. George Huntington Williams, but he's not nearly as famous as she is. But anyway, so another good reason to read the book. You'll find out ideas for paper topics. By the way, you need to have some paper topics into me soon, right? Okay, Then they have key terms. Now this is about normal, maybe a few more than normal. Unfortunately, they do them alphabetically, but they do put in parentheses the pages where they're first defined or first described. So those are good things to go back and review. Make sure you know what they mean by those. Oh, there was summary of equations. Summary of the text here, but then summary of equations here. Now this one only shows one equation. But, oh, and I didn't do this. Well, I did sort of before. Any equation you have like this, you can come up with two others, right? Rho is equal to mv, m is equal to rho v, v is equal to m divided by rho, right? So you can use them in many ways. So it's not just one equation. So that's just one basic one that you can get others. But, now most chapters more than this one, but applying the concepts. Here there's 44 of these, multiple choice. Now most of the subsequent chapters, most of your test questions are going to be multiple choice. They will not be these questions, but they'll be covering the same material as these questions. So to me, this would be the very best thing to study for the test because they give you the answers at the end. So go through these, you come up with your guesses, compare your guesses with these. If you got them wrong, go back and figure out why. Like find those terms over here, go back to those pages and look for them. If you argue with them and say, no, I'm certain I'm right, bring them to me and we'll figure out. They may have made a mistake. In the earlier editions, I found mistakes in them. I haven't looked at these much lately, so I don't know if they have mistakes here. Then they have questions for thought. Here there's 10. Most chapters have more than that. Read through these, think through these. If you understand what's going on there, you're in good shape. Then they have for further analysis. This chapter has 7. That's probably a bit more than most of the chapters. Read through those as well. And then there's some other things you can look at. The parallel exercises are generally great to look at. Like this first test is going to have several math-type problems like we did in class. So if you can do these. Now if you wind up with this book, the big thick one, the Group A parallel exercises have answers in the back. If you have one of the little books, unfortunately they didn't print those. That's one thing I got sort of mad at them on. They did not put those answers in the back. But if you need to see answers, I can copy for you, or you can take pictures of the answers in the back. You all got cell phone problem. Okay, the Group B, though, don't have answers in the back. So I would definitely work on the Group A questions. All right, any questions on what we've done so far? So we've been here about 2 hours. Did I hear that you wanted a little break? Okay, let's take a quick break. Try to keep it less than 5 minutes if you can, fewer than 5 minutes, and then we'll come back and we'll get started on Chapter 2. I talked too much today, so we didn't get as far as I really should have, but we'll get started on Chapter 2. At 3:45, I've got to call roll again, so remind me of that. And I'll also pause Screencast-O-Matic. Our chapter number 2 is on motion, and it's coming up now. This is where I think the real physics comes in. The other was a lot of blah, 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 okay? But motion, core concept, for those who weren't here before, in your text, they put the core concept in white print against a yellow background, which makes it really, really hard to read. This is a lot easier. A net force, which we haven't defined what that is yet, but you probably have a close an idea, is required for any change in a state of motion, period. A net force is required for any change of a state of motion. Now, we haven't talked about what we mean by state of motion or change of state of motion or any of that, but what is motion? Okay, something that was in one place winds up in some other place. Motion had to occur. Okay, now for that to be, that means that you had a displacement, you moved some distance, and always it took some time for you to do that. Okay? It's not beam me up, Scotty. Even that took a little bit of time. Okay? So what we'll do with motion, we'll talk about describing motion, then we'll talk about explaining motion, and then we'll talk about some applications of what we've talked about with the description and explanations. That's basically the 3 parts of this chapter. Okay? Let's start with describing motion. Basic concepts are As I said, you've changed position. You were here, you wound up there. Okay? Position. Now, it took you such a distance to go from here to there. It also took time. What's the combination of the distance and time? Speed or velocity. Now, in everyday English, we use those two terms interchangeably, as if they're the same. And for everyday English, those purposes, they're perfectly fine. However, in physics, we try to be a little more precise. Now, I also threw out earlier, when we were talking about position, I threw out the concept of displacement as opposed to, but distance. Now, those sound like the same concepts too, don't they? There is a minor difference, and we'll talk about that. And then the third concept, besides position, which involves displacement and distance, second is speed and velocity. Then the third one will be acceleration. We'll talk about each one of these separately, so I won't go into too much now. Okay? Now, these are not the applications we're going to do at the end of the chapter, the application for describing motion now. We'll look at three different ways of motion. We'll first look at one-dimensional motion horizontally, moving across the floor here, assuming the floor is level. Horizontal motion. They say on land, on a surface, whatever. Next, we'll look at vertical motion, something moving only vertically. That is a little different. It's one-dimensional, but it's vertical. Then we'll look at compound motion, which is two-dimensional motion. For instance, shoot a basketball. You give, unless you're dunking it, that's one-dimensional motion. I don't dunk. Okay. So, I can't jump. Okay. So, we'll go, not that funny. Okay. The two-dimensional motion, you give it a displacement horizontally and a displacement vertically. That's our compound motion. The first lab will deal with describing motion, and it'll be mostly one-dimensional motion. The second lab will be two-dimensional motion. Okay? Then we'll get into explaining motion. Okay? The basic ideas behind this one are going to be forces, we mentioned in our core concept, inertia and mass. Okay? They put those together even though they sound like they're very different. They definitely are related. And then we'll look at Newton's three laws of motion, and that will be a section by itself, each one of those. And we'll look at applications of that, and this will be the last part of the chapter, and this will be momentum and impulse, circular motion, Newton's law of gravitation, and with that, Earth satellites. Okay? So that's the layout of how we're going to do the chapter, without getting too specific yet. Okay? So let's start with describing motion. One way to describe it is to measure it. So, two fundamental components. We just talked about them. What are they? If you have motion, you have displacement and time. Exactly. So there's the two fundamental components. Your change of position, okay? Notice they called it position. I called it displacement. You could also say distance and the change in time. Because for me to get from here to there, number one, I've got to move a change of position, but number two, it's going to take me some amount of time to do so. Okay. Now, here we have a car going down the road, okay? And we have mile markers, okay? 1 mile, 2 mile, 3 mile, 4 mile, okay, from the initial position. Now, they're saying, okay, I want to make sure I did turn this back on. They're saying that to do the first mile, it took 1 minute. To do the second mile, it took another 1 minute. To do the third mile, it took another 1 minute. And then the fourth mile, of course, it took another 1 minute. Okay? What can you tell me about that motion?
It's constant.
It's what? Constant motion. Excellent way to refer to it. Constant motion. You're not varying the motion. Now, what's not varying?
Speed.
The speed. Constant motion means constant speed. Okay? constant motion, constant speed. Okay? At least that's the assumption. Unless you rush up there and then stop, and rush up and stop. You could do it that way, but generally we're assuming this is going at a constant speed throughout. Okay? Now, 3 important combinations of this length and time. Okay? Change of position is a length measurement. Change of time is a time measurement. Okay? And by the way, when we say change, I'm going to use a certain symbology that hopefully you'll get used to seeing. But I've taught this course before, and I've had people write at the end of the course, what does this mean? I thought it was clear the whole time because I've used it the whole course. So I'll try to be sure. The first of these is speed, and you already threw that term out here. What would you say speed is? How would you describe it?
How fast something is moving.
Okay. And how do you get it?
Distance and time.
Distance divided by time. Just like one of those triangles again, right? Distance, velocity, times time. Distance on top, velocity, and time down here. Or speed or velocity, distance over time. You got it. Excuse me. What gives that away are your units. How do we measure speed? Kilometers per hour, miles per hour, feet per second. What is that? Always a distance over a time. Yeah. Units are your friends. They help you out. Velocity. Now, isn't that the same thing? Not quite. What's the difference? Okay. There is a difference, and here's what it is. It's the same difference of displacement versus distance. Okay? For your change of position. Okay. I drove this morning here to work, live in south side of Birmingham. Let's just round it to about 20 miles. And I was driving generally southwest. Okay? Now, distance I drove was 20 miles. When I drive home this evening, if I go the same route, it'll still be 20 miles. But what will be different? Direction will be different. Exactly. Then I'll be going mostly northeast. So, distance is just the magnitude, how far I drove. Displacement would be with a direction. I was displaced from home to here 20 miles to the southwest. When I leave from here, I'll displace 20 miles to the northeast and go back home. That's a displacement. Distance is just 20 miles. Same thing here. And by the way, we call a number that just is a number. Okay, it may have units with it, but it's just a number. We call that a scalar. It just scales something. How far? Okay? But when you have a direction attached, what do we call that? Anyone know what that is? A vector. Ever heard the term? Okay. It's a vector. Okay? A distance with a direction. Okay? We usually represent those with arrows. So the length of the arrow represents the distance, and the direction of the arrow is the direction. So, now let's think of this. Speed is a scalar quantity. 60 miles per hour when I'm going northwest or southeast or wherever is still just a number. Velocity, though, is a vector. Notice, speed, scalar, vector, velocity, vector. They start with the same letters even. That just happens then. Okay? Displacement and direction and distance, they are the same letter in neither one of those. Okay? But that is a vector quantity. That always has a direction associated with it. So velocity is the magnitude or the size of the velocity is the speed. This has a direction attached to it. Okay? And then anyone think of what the third one is? Okay. Before we do that, let's think. Now, I think one of you said this earlier. What speed or velocity is a change of position over a change in time. Okay? Now, sometimes in physics we use this terminology for that. The time rate of change of blah. The time rate of change of distance is speed. The time rate of change of displacement, which is a vector quantity, that's velocity. Okay? Change of position over change of time. If that's displacement, that would give you velocity. If it's just distance, that would give you speed. Now, what if your velocity is changing? Does that ever happen? Sure it does. And what do we call it when your velocity is changing? Okay, you're either accelerating or decelerating, which you could say a positive or a negative acceleration, right? So that's exactly the third one. The time rate of change or velocity, that gives you acceleration. And we're going to do this over and over and over in this course. We'll come up with a concept like displacement, like distance. And say, well, what happens if we have a time rate of change of position, or distance, or position, or distance, or displacement? Well, then that gives us a new quantity. Well, on these two quantities, let's say the time rate of change of this. What does that give us? The acceleration. So you got that right. Okay? Now, speed is the change in position with respect to time. More specifically, the change in distance with respect to time. Change of distance over change of time. Okay? Yeah. I think we're going to have to stop there. We didn't get very far in the chapter, but it is time for us to move to lab. So we'll pick up and go from here. Let me go on and mark the roll since I have you all together and the others not. Well, I just put the roll in my book, didn't I? Okay. James, was he the one in Mississippi? Huh?
James
That's
and Jeremy.
okay. So he didn't make it in today. Terrence, still here, good deal. Camp is still here. You were sitting here. I keep looking at where you were sitting. Slim didn't make it in today at all, right? And Dart is here. They told me about that. I didn't make it up. Okay. All right. Mason is here. Samuel is here. Ryan, his stuff's here. Okay. Okay. Alfred is here. Jeremy didn't make it in today. He's the one that is in Mississippi. Okay. And no one knows Jalen Kimon Roby. Is that right? Okay, not here yet. Charles is still here. Brittany had to leave. She had to go to work today. She's going to try to get them to change her hours. Trevor, okay, that's okay. And Terry is still here. Okay. Now before we head to the lab, let me just get 1, 2, 3, 4, 5, 6, 7, 8, 9. 5, 4, 9. Got it. Good to have science instructors who can count. Okay. Here's a lab, and like I said before, don't let it scare you, but it is the biggest that we'll have. Maybe not the most pages, but pretty close to the most pages that we'll have all term. Okay. You want to take one? Here it is. Brittany, I'm sorry. First lab. Now, I'm going to mark you here before I forget it. Ryan, right? Okay. All right. Now, y'all can be reading the lab if you want to. You will have to. And it's going to take me just a few minutes to get disconnected here and move down the hall. Where we're moving is just, we'll go out this door here, get into this hallway here, the very first lab on the right. It's 253, we're 255, very first door. It's a little ways down there, but not too far. So You can either sit here until I'm through, or you can go down there and start setting up there if you want to. It's just going to take me a little time to get disconnected from the projector and move my thing, so I'm going to pause. All right. I'll be repeating this, so don't worry about it. Each team has 3 circles. They've got paper to draw them on. They're drawing the circles. They've got rulers. They're measuring the diameters of each circle. They're turning to page 23 of the lab, and they're putting the diameter of the small circle, diameter of medium circle, and diameter of large circle, and they're sharing the data with one another, so they wind up with 3 measurements of.
Since we're a group of 4, how many circles should we have on our?
Okay, you should have 3 smalls, 3 mediums, and 3 large. You may have drawn extras, like I don't see but 1 small, 2 smalls. So one more person will need to draw a small. You got plenty of mediums and large. So record yours. Now, of course, yours is going to be different from the other tables because you have a different large circle to measure. Okay? Everybody got the 3 measurements of small circles, medium circle, and large circle. Put them on page 23. That top line diameter. Second. Yeah, the 3 trials here. One of you view trial 1, 1 trial 2, and 1 trial 3. That's your 3 small, 3 medium, 3 large. So your small, his medium, yeah. Got it. So you're working as a team, so work with each other, talk with each other. Don't expect all of them to be the same, but you did measure in nearest 1/10 of a centimeter, right? Not inches, right? Okay. Okay. Have you recorded them on page 23? Okay, again, they should be close, but they don't necessarily need to be the same. In fact, it would be really suspicious if they were, wouldn't it? Huh? Right. All 3 of you have to be equally really good at measuring, right? It doesn't matter, yeah. Okay, yeah, the way it sort of does. Because when we do the circumferences, they need to match the one that you're doing. So if you do 1, 2, and 3, you know who 1 is, know who 2 is, and just know which one 3 is. Okay. No. On page 23. Okay, at the top. Okay. Yeah, y'all keep up with which small you're using. Each one of you did one, so you do any order you want to. 1, 2, 3. You put your diameter, 1 diameter here or 2 diameter here. So be sure you get them. You keep them. Yeah. Now, if you record them in different order on your paper, just make sure you know what order you're doing, and make sure you get the same circumference with the diameter. Okay. Okay, is there any questions so far? Does everybody have the 3 smalls, 3 mediums, and 3 large diameters? Okay, let me know when you got them done. You do?
We got 3 large, 3 small.
Okay, you're number 3. Okay, you get one of them. You be number 1, one be number 2, and you get there. Yeah. See, y'all are a team. Okay. Now, the next thing you're going to do, y'all got all yours recorded. Okay. Can I get, even if y'all are still recording, can I get your attention up here to this side? Okay? No, here's how we do it. Put the, y'all did do it this way for your art, right? Okay. Give me one of the longer strings. Okay. What? Okay. This is where art comes in. It's art and under science. This is almost more art than science. Everybody got the diameters reported? Yeah, that's what we're gonna do now. Pass them out, pop this in. Okay. If that's the shortest string, why don't you do the medium string right and use the short one, the smaller. Yeah, oh yeah, you're really good. You're really on top of things here. Okay, you got them recorded? Or if not, at least come look. You can go back and finish the recording. Come look. Here's how we do circumference. Really hard to measure circumference of the circle. Okay, so what we're doing, be sure this is down, and especially this one that's rounded like this so it stems right up. So get a place that you can fix this, and then get this out of the way. Okay, and then what you'll do is the very best you can, I'm all thumbs, take this, and for the large one, you'll probably need to use the meter stick. That's why it's here. And you measure that to the nearest tenth of a centimeter. Okay? You'll do it with all three of them that way. And so I'll let you get going on yours again. Okay, you see what's happening? Okay, you'll need the wrong one. I think yours is more than 12 inches. Okay? This table that doesn't have one of those big ones, you can all use your ruler if you want to use a stick. Yeah. Okay? So measure the circumferences. Okay? And you'll do the same thing as you did before. Pass the ones around so that each one measures each one once. And you record your circumference with your diameter. Does that make sense? Are there any questions? Be sure you measure in tenths of a centimeter. Okay. If you have questions, please ask. I can tell already this is going to be a good lab, folks, because y'all are getting right to it. You seem to be catching on real quickly. If you have questions, please ask. Yes.
Why don't we use the formula to find circumference? Like if we know the diameter, then we can figure out the radius. Why don't we just go ahead and use the formula to find
What formula would you use?
There's a formula to do it.
Do you remember the formula? Use your screen.
Well, I did until you put me on the spot.
Okay.
I got my phone, I can figure it out.
Here's why. Because what you're going to do is look at the ratio of the two, and that ratio is going to be the number you can't pick up right now, and that's what you're going to be determining.
So which
Oh,
Sort of the same.
you're gonna need that. Is this the larger screen?
Yeah.
You're gonna need that.
I haven't made one.
Yeah, no long screen?
Huh? Okay. So that was a good idea, but that's what we're looking for.
What, smacking me in the head?
Huh? We're looking for that ratio. Oh, to smack him in the head? Maybe that too, but later. Okay. After I'm not present, because I don't want to have to write up any reports.
Too much paperwork?
Y'all have enough to keep going for a little bit. I need to go get something from my office. Any questions? Okay. So I'm going to put this on pause just for a moment while I'm gone. Okay. So they've been given, each team has a bunch of cubes, and they're first measuring the size of one cube, length, width, and height. And what you're doing is measuring one side, calculating the area of one face, multiplying by 6 faces. That's the surface area of the cube. Then the length times width times height, they all should be the same. That should be the volume of that cube. Has everybody got those recorded? Okay, put units in for me. Yeah. Square. No. Wait. The surface area is square. The volume is height. Okay, yeah, but first do the small cube. Do the surface area and volume of the small cube.
How many places you want us to take?
How precisely can you measure? Yeah, but how precisely could you measure the length?
2.5.
That's all you got. Okay, well then, I would do 16. Yeah. Well, because you only got 2 digits, don't you? Well, if you already did 37, what? Is that your surface area?
Yeah.
Okay, then put the square, centimeter squared. Okay, and then do 3 digits, do 15.6. Yeah, cubic centimeters, right. Okay? Everybody got the small one done, surface areas? Okay? Okay, 2.5, that's as close as you can get. Okay? Then that's going to be one edge. One face will be 2.5 by 2.5. So you multiply that out to see what, that's one face. Then multiply that by 6, because you got 6 faces, and that'll be your surface area. No, 2.5 by 2.5 times 6. That's what goes in the surface area. Right? And then the volume will be 2.5 by 2.5 by 2.5. Okay. Whatever that answer is, multiply by 6. Okay. Everybody getting somewhere? Okay. Y'all got it. Okay. Now, the next one, the next size cube. You can each do this if you want to, because you got enough cubes. You're going to be a 2 by 2. Put it down. Okay, 2 by 2 that way. Where do you get 2 copies? Really? Okay, I think y'all are done. Okay. Now, that's your medium cube. So measure length, width, and height of that one. And yeah, that's it. It should be the same. Okay. You make a 2 by 2 up to 2. You can measure length by width. That's your surface area. Multiply by 6. That gives you total surface area. And then multiply length by width times height. That gives you height. Except, yeah, that's the problem. It's a lot of decisions. Oh, you could do that. Or you could measure across here.
Well, we already measured this way, so
it should be the same. Not everything's the same. Length times width times height. Yeah, that's it. 2.5 feet.
one separate lot.
Okay.
So instead of three, two and two down, and three up.
Yeah, for the lot, you probably going down.
Yeah, the one I just.
Okay, so the zero, yeah, 3 by 3 by 3, so that's when you all count for together.
It'll be
So take 27.
I got 2.5 on the first one, and 5 on the second.
You ain't got enough.
Okay.
If I had another one of these lots, it was the same.
Exactly, so if you go that way, you I see the analytical reasoning.
So it'd be 7.5.
We gotta combine six to make it large.
What's that?
We have to combine-
You have to, yes, exactly. That's what I said, that's why I gave each table 3 blocks. Because the big one's gonna be a 3 by 3 by 3 by 3 by 3. There you go.
Well, since they're 0.5, you still
keep all the lines, this is, you know,
What's that? You're probably thinking right.
So yeah,
Well, there, but then you need another layer.
we keep each kid on different level.
37.5 times simple.
Median line.
You just said 33.5. You said 7.5. Did you know? This is the way that you just like. How'd you do it?
240. You said 33.
Not let me do it. You let me do it.
Large one is 3 by 3 by 3. So you'll need to combine all 3 blocks. Coming together.
Actually, 337.5, all of these is 338. We only want 350.
Need one more layer up there. You just said the length. Yeah.
It's actually 400. Because what he did is trying to, you try to get the answer.
They should be.
The surface area is about 7 square miles.
that's fine.
Yeah, I guess. Look at size, the surface, that's it.
Okay.
That's incorrect.
All these other numbers, you have to write
Significant digits. 421.8.
That's 40. You want just 3 digits, right?
Yeah, that's fine. out the lab, I forgot something. I'm going to turn this off for right now, but I'll be right back. Okay, I think I had already recorded part of this, but each team has a different container. They're each measuring the best estimate of a length, a width, and a height, and they're sharing with the other two. Okay? Then everybody will calculate the volumes based on the data that were given, and then the mass of the container, you always zero the scale before you take your measurement, and then put the thing on, take the measurement of the mass of the container. Okay, zero the scale first. Be sure you zero. I'm not. Yep, because it measures in grams, so a gram is pretty small. I will try not to sneeze. Okay. Usually a pretty good technique is the one who zeros should be the one who measures, because you know how you looked at it in zero, you know how you looked at it.
He's shaking with the tape.
Okay. That looks like to me it's. Yeah. Okay. Right. Or
That's in grams.
Yeah. That's in grams. Measured in grams. Okay. Well, have you done your dimensions? Shared the dimensions. You don't have to do the calculations yet. It's only to do your measurement of your mass. You can do it, it's fine. It doesn't hurt to, but I was just trying to get the measurements done so we can move. Oh, y'all think you're good on your circles?
Yes.
Let's just get these out of the way for now. Y'all want to hang on to any of these papers? The reason I'm moving them is because things do get wet. Does everybody determine the weight of the mass of the containers? Different from weight, folks. Remember. All right. Now the fun part. Now, what I would suggest, yes, we are. Now, what I would suggest is y'all don't wait on these guys. Y'all share the scale with those guys because it's not going to take them long. Now, I've given each one of the teams a plastic container. Y'all have a small one, the other two have this size. Okay, you can, be careful. This water squirts out very fast and hard, so be careful when you do it. Okay. I'd say come pretty close to filling it up. Okay? You won't need it totally full, but yeah. This is just to get started. Okay, that's good enough, I think. Okay? Now, again, whoever's doing your measurement, be sure your scale is 0. Are you confident it is? Have you already done the mass of container? Okay, is this what you got? Okay, now yours is going to tend to close on you. Okay, so you might have to hold it open while you pour water in. After a while, and be very careful. I don't want a big mess. Okay, and be sure you get your last piece as far away from this one. Okay. Yes.
What do you think about that?
Wait just a second, I'll come look, I just found something I needed to put up. Okay. Yeah, y'all have to wait on these guys. Okay. Yeah, you multiply those things. Yeah, right.
What's the measurement on
Yeah,
that?
wait, did you get an answer to that? Start filling the water? Okay, you got it. Okay, share it once. Okay. Now, all the way to the middle.
What's y'all measurement
I
on
think
water?
you'll notice something as you fill it too, won't you? It almost looks like it overfills. Right? Okay, that's good enough.
What, it
Okay.
went all the way around?
Oh, it did.
It must have.
It did, yeah, it must have. Okay.
You don't know where zero at when you raise it
Okay. So that's 500 and whatever.
We got digital scale.
Well, this is a cheap
Zero
one.
would be 500, so.
Get your measurement.
We'll let you-
And as soon as you get, okay, now, what you do now, wait, okay. No one? Okay. What you do once you fill your container, dump out this one completely. Okay? And what you're going to be doing is then emptying that container back into here. Okay? That is going to be the tough part. Okay?
Hey, what more's got a crack in about halfway up?
Okay. Try to do it. Okay.
Keep putting water.
Yeah, I tried to taste it. So pour quickly and measure quickly. Okay? Alright. Now, let them use the scale. In fact, if you want to move the scale, y'all can go and
Now,
do
do
it.
we need to, do you have to
I was
zero
in the way
out?
in case I dumped the water.
Okay.
120 for the.
That's massive water plus. Okay. Okay, that's all right. That's pretty. Okay, did y'all measure all that? You want to try it again, or are you happy with your measurement? Okay, remember you may have some
How
experimental
much
errors.
did y'all come out with? You said 505?
Right, yeah.
There was, see, it was coming over the rim, but there's a little bit part of it.
Okay. Okay. Now, there's paper towels over there, so, wait, yeah, okay. Oh, wait, wait, is that what you poured from there?
Yeah.
Okay, you tried to get it back in there? Okay, that's all right. This wasn't filled before, right? Okay.
Yellow water there. Yellow stuff.
We're not friends, like you.
Okay. The cutting down your experimental error. Okay, now, the two teams that have already somewhat gotten your water, what you do with it from this is pour it into here. Now, don't over pour past where the line is, and you will need to pour into both of these containers. That's why I went and got your second one, because just like it went over the scale there, which I never had it happen before, so too this will go over here. Doesn't do you any good to get water up here. Right? You need to keep it within the scale. You can get them there too. I would say. Right. But just don't go past the markings. Okay?
You gotta keep your finger out.
Fairly steady hand, but.
I had a crack in it, that's where.
Oh, that's
came out
it.
the crack. See,
I thought you
that was
took
wrong.
the lead. No, I'm sorry.
Open that up like that right there. There's no wind.
Okay.
I had a little bit too.
Now, what you want to do then is measure the volume of water here. Okay, you don't have to get exact, just get it so you can measure it and then pour some. You won't overfill the other one, I don't think. So y'all have got more in it than most have. Looky there. Okay.
Oh, 190.
All right. What I think I'll be doing while y'all are doing that is collecting stream.
That's a milligram.
All
was that in?
one,
It'd be measured volume of water too.
yeah, what you just did was volume of water, and is that in
What did y'all come out?
milliliters, and that's exactly what you're measuring there. Okay,
460.
can I get you free stream?
We're still under 60 milliliters. Big block 460.
Like you want to add like.
What y'all give me y'all, measure volume of water? When y'all measured in that thing right there.
I got 112.
112?
What's the
That is
name?
12.
Oh, so I never
Yeah,
checked.
it's very close. Yeah.
Is that guy grams? What you get grams? Line 7?
Oh, yeah.
That's 1.6.
Yeah.
Yeah, that also.
All right.
So they know that?
Yeah, they can ask me.
112.
Okay. So has everybody got all the measurements you need from all three teams? You'll do your calculations now. Now, okay? Okay. Don't get caught up. You added these two together, right?
Yeah.
All right. Now, let's talk about calculations. Do you want to continue calculations with the one you just did and then go back, or you want to start at the beginning? The one you're on, okay? So, each team has gotten from the other team, and you made your own, your lengths, widths, and height. You multiply those two together, the calculated values. Probably you've already done that. If not, do it with the data they gave you or you collected. You got from each team the mass of the container, and the mass of the container and the water, right? So what do you do to get mass of water? Subtract number 5 from number 6 on all three, right? Then you each got a measured volume of water from all three. Except this is in okay, never mind, okay. In milliliters. Okay. Now, what you do on number 9 is the ratio of the calculated volume, that's number 4, to the measured volume, that's number 8. And you do that for each size. See what's happening there? Number 9 is ratio of calculated volume, number 4, to measured volume, number 9. Do it for the small, the medium, and the large. Right? And then your ratio of mass, number 7, to the measured volume, that's number 8. So the ratio of 7 to 8. 7 divided by 8. Remember, the ratio is the top one divided by the second. Okay, any questions? Okay. What's your question? Okay. Let me just see. Yeah, that looks good. Now here, measure volume of water. You should have got those from each team. You got one, didn't you? Yeah. Okay, did y'all get it? Did y'all get a measure volume from that thing right there? Oh, here's. Yeah, you got one. Okay, they didn't get yours. Now you did keep. Okay. I'm afraid you got numbers. I'm not sure you got them. See, to me, this is small, and that's small. This is medium. Yeah, but I think you switched the group numbers. I think, I'm not sure.
No, see, that's what I got. See, we didn't need meeting group. I got that.
You gotta ask your.
No, we do 4 and 8. 4 and 8.
Okay, somebody has made some motions wrong, I think. Okay, they're coming out okay, I don't know. Okay. Huh? So the heights are too far off from the tree. Let's check this. Okay, here's something, listen. Oh, okay. Who is medium, this group? Yeah. I think your medium height you got wrong.
Which one?
Is this you? Do that height again.
Yeah. Oh, that's 3.
The height on the medium. Okay. Okay, someone wrote down.
I wrote down mine wrong.
Okay, and that's who you copied. Okay.
Thank you. Appreciate it. The correct answer would be
Okay.
3.5.
On the medium, the height is, what was it?
3.5.
3.5 centimeters. What's that? Yeah, but it's okay. I can do that.
You can put him in that.
Well, no, it's only gonna
Line
take that and
number
that.
4 over line number 8.
Yeah.
You gotta write the units beside it.
What do you have for the height on the top?
The height for which,
For the meat.
3.5.
Well, that seems a little high, doesn't it?
190.
3.5 and 3.1. All right. Did all 3 teams get the corrected height for the medium? Was not 1.5, but you said 3.5?
Yeah.
This is a bit tall, but I don't know. It's closer. Okay. In other words, the volume should be small, medium, large, going up in volume. Okay.
Now the ratio
This,
of the mass of the water.
Okay. Are there questions?
I just got a question.
Calculating volume for volume. So that one will be changed to help. No. Calculate it and just divide by that. Always the one mentioned first, divided by the one mentioned second. Yes. And that goes there.
Yeah, I got 1.24. Check that right, of course.
Question.
taking what's in line 4, see? Volume on the top, line 4.
Okay.
133 over 112. So each one of you know, line 4 on top, line 4, line 8. But you gotta write the numbers. They're different units, so that's why you can go. If they were the same units, then you could take them from.
I'm sorry.
We're not dividing them into each other.
They're different units.
Say that again.
This is like miles per hour.
Are we just stacking that on top of that and writing right there?
This divided by that.
So it'd be 1.24, and you just got those two outside.
Yeah, because this is centimeters per cube. Centimeters cube per millimeter.
Oh, so you want us to reduce it down?
Huh?
See, when I wrote it, but I didn't.
Yeah, divide it.
Oh, you want us to reduce it on that?
This number divided by that number, and that will be that unit. See, they are different units.
Okay, so.
You just fill in the number. Do the division. Right or no? Okay. Yeah. What's that? Yeah, you can. It's only if came up really big discrepancies then. No one feels like they need to do any measurements again, right? I mean,
Just calculation.
math measurements, just doing calculations. All right, you ready to do more calculations? Okay, now, if you turn back, since we're doing the third one, the part C, you've done 1, you've done 2, you've done 3, you've done 4, you've done 5. Now, I think we're ready to do number 6 on top of page 18. Make a graph of the mass in grams, the row 7 data, and the volume in milliliters, row 8 data, to picture the mass per unit volume ratio found in step 5. Okay? Which is the one you just did. Okay, put the volume on the horizontal axis and the mass on the vertical axis. So the graph paper you'll find is on the back side of page 24. Okay? And you can do it whichever order you want to. I would say, what did it say? Mass down here and volume here. I believe that's how they said it, right? Yeah. Mass horizontal, volume vertical. Oh, okay. Okay. Yeah, that's
Volume
right.
on the
Yeah, mass vertical and volume horizontal. Exactly. Okay? Now, you'll need to decide your scale. Someone give me, because y'all got the same data, right? Give me the max min of your mass and your volumes. Huh? Okay. You're doing mass vertically, right? So tell me what your mass is, the largest and the smallest. Mass, yeah, right here, number 7. 113 to 476. So 1, 2, 3, 4, 5. Yeah. You can do 0 0, 100, 200, 300, 400, 500. And then this way, 0, 100, 200, 300, 400, 500. If you need 600, you can go up to there. You got plenty of room. Your mass is vertical, your volume is horizontal. And do each big block is 100. Okay? Believe that'll get you on there pretty well. 100, 200, 300, 400, 500, 100, 200, 300, 400, 500. Second? Yeah. 100, 200, 300, 400, 500, 300. 100, 200, 300, 400.
That's about the math that you do now. You can say like that, right?
That's fine.
The dark line. Mass is number 7. So you'll pair 7 and 8. That's what you're doing. Yeah. You got it.
I know.
Right, okay. Got it.
Mass,
Body
vertical,
points up. Huh?
masses.
Mass vertical and your volume horizontal. Exactly. Are we plotted? Okay, start plotting. Yeah. Using row 7 and row 8 data.
Yeah, but we put all three on the same graph, so some of them lines been on top of each other.
Okay. Plot the points. Okay. This vertical you want 13, horizontal you want 12.
Oh, where they need it.
Yeah, right. Plot a single point for each of your 3 containers.
Each square is 100.
Each big square. So that I think will work pretty well. Got them plotted? Good deal. And you can even draw the line. Okay? Calculate the slope. Yeah. You use the straight edge and you draw it right. Probably a little better to use the straight edge because I have them on the table for you, but it's not far off. And I think they line up pretty well. They line up pretty well. So I would take the top and the bottom. Okay, and calculate the slope, difference in y of the difference in x. Right? This one's that, this one's that. That's it, yeah. Yeah, see how handy that math is? Oh, no, you keep it. Okay, you didn't rent it, you bought it, okay? Okay, trying to destroy my meter stick, huh? I got you.
It went down my phone.
I see. Mind of its own.
All 3 lines should be the same?
Oh, what?
All those should be lined the same?
Well, they should be close. It'd be a little suspicious if they lined up too perfectly, wouldn't it? So you get your best line to connect the best, those 3 points, the best. Wait. Minimize your error, okay? Now, if it helps, see if you can go through 0, 0. If it doesn't, don't. Because 0 should be 0 mass should be 0 volume. Alright. And since those line up so close, I would just take the value here, the y value here, minus the y value there, that's right. Difference to x is equal to right. Okay, then take the ruler, draw the best straight line through those 3. Yeah. Yeah. Vertical and 112 horizontal.
What if the line not really straight?
Yeah. Just to both sides. But go on Yeah.
Oh, what's the, you don't have to plot it, you can take your, go through your lines, subtract them.
Yeah, that's all right, yeah. If they line up.
Yeah.
And of course they do.
If you got two of them, they are.
Yeah, two always do. Okay, you got that one, then you do the next one. Yeah, somebody's been, doing real careful measurements. What's that? What's that? Okay. Well, no. Divide. Okay. Did you write it down? Okay. Yeah, that's exactly what I want. Okay. For those who have gotten this far, see after you, on number 6 on page 18, you made a graph. Number 7, you drew the straight line as close as possible to all 3 data points. And you could use the origin 0, 0 as a 4th point if that helped. And then calculate the slope of the graph. And that's rise over run. Change of y of your vertical over change of horizontal for your run. Bless you. Again. Second. Okay. You got 0.9. Okay. Now, what it says, use that as the. Now, I hate to write on the board because it looks like they got something important here. I'm going to go get a marker and I'll come back and do that. What's that? Going to talk about all the calculations to make at this point. Okay? On your table 2.1 on page 23, the top part, you did diameters and circumference. Now be careful here because look at the ratio they're looking for. They're looking for circumference over diameter. The second one divided by the top one, right? C divided by D, not D divided by C. Even though D's on top, it's always C divided by D. So you got the numbers there, do the calculations. C divided by D. Circumference divided by this number divided by that number. All the way across.
Is this still the same unit?
What's that?
Is this still the same unit?
Units cancel out.
Yeah, okay, yeah. The units cancel out. Very good. Because these were in centimeters, the other was in centimeters. So it's a pure number. Okay?
So there's not going to be any units. No,
Did you get your line?
yeah, no units.
Was it pretty good? Oh, look at that. Okay. Now, since it went through it went through all 3 points really well. So, since it went through those exactly, then the easy way to do your slope is do this minus that divided by this minus that. That should give you your slope. Let me see how your numbers are looking so far. Not bad. Not bad. What do you get? Let me see that. All right.
How about the average? You want just one of the circles or add them all up?
Okay, add them all up and divide by 9. Yeah, add them all up, divide by 9. What's that? Yeah, it says on here, it says, back on question number 8. Calculate the slope of your graph on page 18. Calculate the slope of the graph and record it right there on number 8. And that would be in units of what? Ground all the way or ground to keep the center? Or ground floor? They mean the same. They are the same.
How can we tell what the area is?
What's that? Yeah, divided by 9. Added those together and divided by 9. So you have to have 9 numbers. You should have something pretty close to 3.7. I think you divided by 9 twice. The number you had up there was pretty good.
How do we calculate experimental error?
Okay, experimental error. I just erased it, but it's measured minus actual. Right. And your measured was. Oh wait. Oh, here. Okay, wait. Yeah. Here. What is your actual? What you expect the ratio of your diameter to your circumference to be?
3.14.
Why?
Because
It's pi. Exactly. That's the number you're looking for, right? So 3.14 is your expected.
So we
So-
subtract pi from that?
Yes, exactly.
No.
Yeah, exactly.
Just with
Yeah, that's where the light comes on, right? Okay. It sneaks up on you sometime, huh?
We got 0.03.
You got what?
0.03.
Error? Not bad. Okay. Okay.
We got 0.078.
Not bad. Okay. Okay. Yeah. Circumference divided by, so this number divided by that. This one divided by
What you get
all
for
the way.
your, 3.22 is what I got. I subtracted that from pi. I took it 3 digits.
Okay. Y'all ready for the second calculation, set of calculations? Down here on area and volume ratios, it says what the ratio of area to volume. So top line divided by lower line. All right, that. Top divided by bottom. Okay. Okay. Now, yeah, the units don't match up here, so you can just leave off units for the ratio. It'd be per centimeter would be on the bottom. 1/centimeter. So they don't mess with the units, so we won't either. Just do the numbers. There you have an accident right there. She was drooling over the experiment. curious about those.
He's seeing it as it gets bigger.
Yeah. As the cube gets larger, the ratio actually gets smaller. Interesting. Okay? You could go back to question number 6 on page 16 under area and volume ratios. Describe a pattern or generalization concerning the volume of the cube and the surface area to volume ratio.
Larger cubes, what you call it, inverse.
Yeah. Yeah, it's an inverse relationship.
So just be right inverse relationship or
Write something that makes sense to you, as long as it's correct. Yeah.
6 on page 16.
And after you've done all those, you add all these together and divide by 9. And that's what you add.
And the volume increases the ratio.
The ratios, yeah. So the terminology, right?
Good.
I wrote it in inverse.
Volume increase, the ratio decrease, so they inversely proportional.
Yeah. Yeah, that sounds reasonable.
Military time. They want to get up. Old 400, we get up.
How are we doing? You waiting for something else? Okay. Now. Okay. If you go to, and you were asking about this, on page 18, you still got 2 questions to answer there. The density. Hopefully, if you can't figure out that one, talk with me and we'll talk it out. Okay? Number 11, you can wait till the whole thing's over with, or if you think you already know the answer, you can put that in. Now, here's the biggie. This lab is the only one that has something like this now. In addition to everything you just did, on page 19 and 20, there are 7 more questions under results. That's a generalization. Some of those answers you can find at the writing at the beginning, and others you'll have to conclude from what we've done. Okay? So answer those, what did I say? 7 questions. Say again? Oh.
The other one,
18 and 19.
the next
That's
7
7.
questions
And then there's problems. Okay? These problems have nothing to do with the measurements you just made, but they're similar type things. So here we have 7 more questions. Now the first few problems here, in fact all these, are going on this one block here. 1 meter high, 2 meters deep, 3 meters across. Okay? The first question there, calculate the volume of that block. Okay? In cubic meters. But then the second question is, restate those dimensions not in meters but in centimeters. How many centimeters in a meter? 100. So that would be, what would those 3 dimensions be? 100 by 200 by 300. Very good. So you got that one done. Number 3. Make a sketch of the aluminum block and show the area of each face in square centimeters, not meters, square meters. Okay? So basically your sketch will look just like this one, except you change the units. Okay? In fact, if you want to use that, you can use it. But just make this 100 centimeters, 200 centimeters, and 300 centimeters. Then label me on top of the block, an arrow going from there, showing what the area of that face would be, of the end face, where it says one face, what that area would be, and the front face. So you calculate that in square centimeters. Okay? Then you do the volume of the block in cubic centimeters. And by the way, put your answer under 3. You might do your drawing over here, but put the answer over here under 3. And then number 4, calculate the volume of the block. Number 5 is a little strange. If you turn back, you'll see at the beginning of that, it says problem. You said aluminum block that is 1 meter by 2 meter by 3 meter has a mass of 1.62 times 10 to the 4th kilograms. Question number 5 says, what is the mass of the block in grams? How do you do that? Say again? How many? 3. Which what? Okay. Actually, you're going to a smaller unit, so you'll need a bigger number. So, yeah, to the right. So that's just 3 more places, so you can leave it just like this, only change that 10 to the 4th to be a 10 to the... Add 3? Huh? Say again? It'll be 10 to the 4th to 10 to the... That's where you add 3 to. 7th, right? Well, 10 to the 7th, that would be 16,200,000, right? Grams. Okay? Right. Or you can leave it in scientific notation if you want to. It's up to you. And then number 6, what is the ratio of the mass you just did in 5 to the volume that you calculated in 4? And that has units. You better put them. And then you should figure out how to answer number 7. Now, if you have trouble with any of these, get with me and we'll go over them. Okay. So here's the clue or the key, folks. Starting from the beginning, page 15, verbiage, but number 6 needs an answer. Anywhere you see a lot of white space, it needs an answer. The others are instructions. Number 6 needs an answer. Then verbiage. Number 8 needs an answer. Most of you have already filled that in. This is on page 18. Number 9 needs an answer. I think most of you have already done that. Number 10 and 11 do need answers. Don't leave any big white space blank. Then 19 and 20, those results, those 7, all need answers. The problems, 1 through 7 there on 20 and 21, all need answers. And then make sure your tables are completely filled out, every block is filled in, and that you have a graph on the back. When you have all that done, your lab's complete. I'm guessing not. It's all probably not complete today, is it? Okay. So why don't we, first thing Tuesday, if you've had any questions in how to fill out the lab, we can answer those on Tuesday. I'd like you to have worked on this over the weekend because your test is going to be just like this. In fact, it's not going to be nowhere close, but the concepts on your test are not far from what the concepts of this are.
Where do we put the sections?
What's that?
9 sections.
The name is all you need. The date, if you want to put today's date, is the 9th. Is that right? 8th. Okay, the 8th. Here on my computer. Yeah, no, today's the 9th. Yeah. Okay. Now I feel really bad. I feel like I've cheated you out of 5 minutes of your tuition dollars here. Boy, do I feel rotten.
I got mine for free anyway. Don't feel too bad.
Guess we'll see you next time.
All right. Have a good weekend, everybody.
Yeah, I almost took my mind out of it.
All right. I'm going to shut down this if there's no more